The forum will start in 3 minutes. Please take your seats and remember to turn off your mobile phones or switch to silence mode. In addition, to keep the meeting room clean and comfortable, please don't eat or drink here. Thank you very much for your cooperation. Good morning, ladies and gentlemen. Welcome to the opening ceremony of 2023 International Forum of High-Density Plasma Coatings and Process Control. This is organized by Dayong Vacuum Equipment Company and Fengjia University. We are honored to invite Guo Haochang, the Vice President of Fengjia University, to give us welcome remarks.
Sorry I'm being late. Okay, and President Yang from Dayong Vacuum Equipment, and our delegates from all the way from Germany, and all these distinguished delegates and participants, welcome to our campus, and good morning. I think it's my great pleasure to be here in the opening session of this 2023 International Forum of High-Density Plasma Coating and Process Control. And I think it's a very unique situation that we, after 2 years of pandemics, that finally we can sitting together physically, face-to-face, and have very effective interaction between us. And then at the beginning of the forum, I would like to thank you, our long-term partner from Fraunhofer, IST, and without this Germany, Taiwan bilateral joint project running for many years, and this forum would not be possible. And to this end, we also like to thank you, our long-time support from Dayong Vacuum Equipment, and President Yang, you have our sincere appreciation, for your long-time friendship and support. Okay. And then coating is a very intriguing, ubiquitous technology. I say ubiquitous is everywhere, But it's interesting that the coating technology itself cannot be delivered as a product. However, any high-tech product cannot be delivered without this technology. Okay. And then nowadays we heard a lot about like 5G, digital transformation, AI, metaverse, AR, VR, to name a few. And the list can go on and on. However, all these virtual world fancy applications are based on physical manufacturing. And recently we heard a lot of stories about ChatGPT from OpenAI. And it seems like if we have a very, very powerful AI, then we can solve all the issues, all the problems of our daily life. But don't forget, this virtual world still built on the manufacturing in a broader sense. And then for today's high precision manufacturing, vacuum coating or coating technologies are actually one of the key technologies. It's an enabling technology. Okay. Don't make me wrong, I'm not saying AI is not important, but I'm saying when we focus on a specific technology, we tend to ignore the importance of others. And we are happy at Fengjia University, we still think surface coating technology, a very important one, our strategic point for our university's development. So today, I'm happy that we have this forum, so many participants join together, and I wish you a very meaningful and fruitful meetings. Thank you very much. Yeah.
Thank you, Vice President, for your address. Next, let's welcome Yao Guangyang, the President of Dayong Vacuum Equipment Company, to give us welcome remarks.
Ladies and gentlemen, welcome to our international forum. Thank you for your day today. My name is YK Yang, the General Manager of Dayong Vacuum. And Dayong Vacuum was founded in 1968. My father, Imo Yang. And during these 55 years, we have been working very, very hard on technological research and innovation. And we have one dream that one day Down Vacuum can stand on to international stage. And I believe today is the first step. And for this important moment, we have to appreciate to Professor Lee, Professor He, and Fongjia University, Fraunhofer, and Plazas, and all of our partners and customers. And with your support, and Down Vacuum will keep working very hard and moving forward. Thank you very much. Thank you.
Thank you, President Yang, for your address. Let's welcome Zheng Zhongli, the Chair Professor of Fongjia University, to give us welcome remarks.
Vice President Tang and General Manager Mr. Yang and Dr. Benfoff and Dr. Sutet. And yeah. Okay, today's forum is organized by Dayong Vacuum Equipment and the Plasma Institute of Fongjia in Plasma Institute, the Institute of Plasma, Fongjia University. And ladies and gentlemen, good morning. I wish today's forum will be succeed. And because plasma is very important, there are 4 states of the matter: solid state, liquid state, gas state, and plasma state. And actually, 99% of matter in the universe is plasma. And plasma also can not only exist in the nature, but also can be generated by human being, by strong electric field and magnetic field. And there are many applications of plasma, like surface cleaning, surface treatment, surface modification, and sputtering, vacuum coating, and you can name that. And in category, you can say you can apply the semiconductor, biomedical, mechanical engineer, aerospace, and also military. Actually, it can exist in the daily life to the scientific research and industry, also in many areas. Today's there are also many technology have been developed and under development. And today's talk of this forum is part of this research. I wish it will succeed and hope everybody happy and healthy. Thank you.
Thank you, Professor Lee, of your address. Now, let's welcome forum organizers, Professor Zhu Lianghe and the Vice General Manager Lai Xingqian, to give a report to this forum.
Maybe I start and give a brief report to you about the status of this forum. Good morning, everyone. And thank you for attending this forum. So please come to next page. Okay, thank you. Okay. Where is the laptop? Good. Oops. No, this is not the slide. The second page of 第二页，或者你帮我切，对，就这个的第2页。OK。 Get it? Okay. So before that, a bit of Daiong vacuum has been mentioned by President Yang. The company started from 1968 when I was young. So I used Daiong's component, have been during my master degree and PhD degree. So that started with component manufacturing. And then goes up to date for integration of a coating system. It's really a huge step from the beginning up to now. So he is very supportive to our academic side. So we were very happy on that, and including today's forum. And so when talk about Institute of Plasma in Fengjia University, as mentioned by our Vice President Tang, we think of ourselves because of the strengths being supported by Fraunhofer IST and all our industry partner process, for example. So we do think ourselves the bridge over the gap of academic research and industry production. So we are happy to help you through any possible solutions for getting promotion. And therefore, before 2 years ago, we then started a full spectra integration and to involve in a project having supported by Ministry of Economic. Today we have Mr. Guo here for a short introduction, and we are honored of this project being granted by the government, and also from German side granted by I believe it's ZIM, right? Yeah. So until now we have some kind of outcome achievement breakthrough, and therefore we would like to share together with our honorable speaker, our former chairman, TACT, Taiwan Association Coating and Thin Films, and President Lee, or should I call Professor Lee, he will be the general chair of ICMC next year. So please welcome to join ICMC next year. And so the target is Industrial 4.0, of course, intelligent vacuum coating with smart control. Thank you for all our partners participating, and those many coating techniques. High density plasma is really what we are looking at, because it provides a better quality of deposited film. And from Taiwan, we do some homework and to see which is very active in this field. And we started to put the keyword high beam, high power impulse magnetron sputtering. And we see that, you see Professor Lee here, who is the most active person in Taiwan. And then allow me to be not humble and place the third position. Okay. And the point is that it's really an active field in Taiwan. Right. So I'm surprised that we have so many delegates from industry today. So this is our foreign program today, just to skip. And because of the schedule is tight, we have 4 keynote speakers and 7 invited speakers just in one day. So allow me to make it quick. And then here's a bit of our venue. So we are here at the nice international conference room. And for lunch, please go to the first floor and the second floor. This first floor, 102 and 104. For exhibition, please visit our exhibitor at the second floor hallway just outside. For coffee break, it's also at the second floor. So this is the floor layout, floor 1 and floor 2. So if you would like to go to have a rest, for washing room, please go to the corner. And room 102, first floor is here, and room 104 is here. Okay, so the status of our delegates today, you see the industry, our delegates from industry goes over half of all our delegates, and 60, and probably 1/3 from academia, and 60 from institute and association people, shares 2, and then an overseas visitor delegates is 7, and with total like over 195. Thank you very much for your attention. And without TISFA, without MIRDC, they all have presenter and also even speakers here today with us. So thank you very much. And so a lot of thanks, but limited time, so I can't give my thanks more to you today. And then, so just last words to Cash. Oh, you got microphone, okay.
Thank you, Professor He. Hello, everyone. Thanks for coming. As one of the organizers of this forum, we also express great thanks to our speakers. Wish you have a fruitful forum today. Thank you.
Thank you, Professor He and Vice General Manager Chen. This is the end of opening ceremony. We would like to thank you for your participation and wish you have a wonderful day. Please, Vice President Tang, President Yang, all our VIP guests, all speakers, and all our participant friends, take your seats and face the stage. We will take a group photo. One more time. 1, 2, chop the temp. Okay. Vice President Tang and some of VIP guests are engaged with business this moment. They will be leaving. Let's thank them for their coming again. No. Today, first talk will begin. Please welcome Professor Zhu Lianghe to host this forum.
Welcome our first keynote speaker from Fraunhofer Institute, Dr. Ralph Bendorf. He is also our chair professor in our department. So give him a warm hand.
Yeah, good morning. Thank you for having me here. It's a pleasure to be back in Taiwan. So after, we heard it before, after almost 3 years not visiting, I think the last time I was here was in November 2019. And so it's really good to be back again and to meet in person. It's just a pleasure. And even over the pandemic, I realized how much I like Taiwan as a country and also coming back and meeting colleagues and friends. So it's an excellent venue. Thank you for being here and thank you for giving me the honor to have the first talk. I would like to follow up on what Vice President Kuo was talking about, thinking production or thinking the production engineering from a different level. So we think about digitalization, we think about digital transformation. In the wording, there are some differences, but in the end, it comes to changing our mindset from the pure machinery to the whole process flow. And I try within the next approximately 30 minutes to walk you through on the example of vacuum coatings. So having a short introduction and then talking about topics like data management, digitalization, what are ways towards the digital transformation in respect of vacuum coating, and ending with some example of a digital twin of a vacuum coating system and giving an outlook in what I believe will be the future of production engineering or vacuum coatings. So already there were some slides on the screen saying that we are somewhere around here, Industry 4.0, having control, automated control, virtual systems, or even cyber-physical systems or digital twins. And we are speaking about the Industry 4.0, the current trend, the situation in manufacturing. We have smart factories, we have interconnected processes that already handle a lot of data. Quite often it's still step by step. And we try to minimize any risks, any waste, and we want to come to a very streamlined production. So one of the things we want to address also with the transformation is to minimize the wastes or to go to a lean manufacturing. And some of those things we also have seen, on the other hand, can create problems like in the pandemic. Of course, it's a problem when you keep all your products in stock and you have to ship it across the globe. On the other hand, if you don't have the parts to be productive, you also run into some problems. But in the end, and I will not go in detail through all the different aspects, we want to minimize overproduction. We want to keep the stock as low as possible and minimize transportation. Also, the poor people that have to go from here to there to exchange data, to do a lot of work. We want to minimize and streamline all the processes. Of course, waiting, we had it in the mentioned project also, waiting for components for a year due to some delivery issues and problems. We want to have perfect parts and we want to produce not beyond what we need and to keep that simple. So there are several aspects if we can close the digital gap. We can have a better utilization of our capacities, of our assets that we have. We can reduce dependency on tactic knowledge, time and cost that is linked to production verification, to quality check, and so on. And we have all our business metrics, especially for the companies, very essential to have the yield cost, delivery, equipment effectiveness, and so on. And of course, there's a lot of things, and in the end, a lot of new business opportunities coming up in that development. And just to make a short definition, and maybe you are better informed than I was. For me, it was helpful not to mix up all the different words. If we speak about digitization, we try to convert from analog to digital. We want to have digital information. That's already gone. If we speak about digitalization, then we want to convert our business processes using the digital technologies to increase the efficiency. And I think in many cases, we are somewhere here in real life or in production. And we have our automated processes. We streamline the processes. We try to connect and make it as effective as possible. But my opinion, where we are heading to be, in some areas we are probably already there, is the digital transformation. And the game changer is that we change our mindset. It's not the engineering mindset, but it's really thinking from the digital approach, thinking about the whole value chain, about how all the interconnection, about all the processes on the digital level, and then design the machines according to all the artificial intelligence software and connections that we have available nowadays, and to incorporate that. Some examples were mentioned before. Already you have robots, you have systems that can write your thesis maybe better than you will write it on your own, but maybe the content yet is not that perfect. We're working on that, so that's also the bright future for the scientists, of course. But that is what we're speaking about. Having a different mindset and thinking from the digital perspective how we can build up the whole process chain. And this puts a demand on all the data that we are handling. So in the end, we want to have something like a cyber-physical system. We have some components in between. I will go more into detail. That's just the motivation. So, and then the digital twin will work, but let's start some steps further. So in some areas, we're still here. So we have our materials, we have all the different processing steps in our production line, and the material goes from here, for example, in plasma for the pre-treatment. Then we move to the next step, modification, coating. This could be even must not be a plasma, could be also a wet chemical cleaning sign or so. Then we go to the coating, and then we do analytics. And on the same, we collect data for this process, we collect data for this process, and we transfer by human the data from one process to the other. And somehow we want to interlink this. We want to connect the data instead of doing everything manually. So we want to have the material flow here, and we want to have the data interactive. We want to log our data. We want to feed it to a central source, to a database. And this also using, for example, artificial intelligence can help us to control our process, to modify the properties, and also have the quality control, and everything will be incorporated. So that's the vision to go. In some areas, of course, you have it in the production. In other areas, you have to reintegrate. And in the end, we want to have cyber-physical systems, or we want to have a digital twin. So from our real world, we want to have a digital counterpart that in real time shows us what is happening. So we have the cyber-physical system, we have the plant control that's communicating with the server. All the data is fed in a database, is operated, can be visualized by a dashboard, for example. And then you have the digital twin on the digital area, also taking all the collected data here, using maybe artificial intelligence, simple models, detailed models depending on the calculation power, and creating a feedback on the output for tailoring, in our case, process properties, film properties, and the coding itself. And some of the approaches, at least what we are dealing with, is that we're trying to be or use open source software to be flexible for everybody, not to stick on licensing or things like that, because you want to be open also for the future for modification. And just to start from the theory and to come to real life, a situation we are facing quite often. You have quite old equipment. One of the benefits is vacuum equipment is that the vessels and the machines are very robust. But of course, time moves by and all the control, you have to refit or retrofit the systems. You want to get all the digital data. And we had an inline coding system where we added some sensors and different modules to just collect data and to make it real-time operational. So a very, very, very simple, low level. In this case, for example, if you would say, we have a process, we have a vacuum process, we go for constant power in different steps, we want to keep that, and we can track all the data. What is the existing current here? You can see there is some arcing event or something like that. You have the voltage, and just by having the data, that's the first step. But the big point is, what do we do with all the data? How can we handle the data? It's nice to have those data. Maybe we also can correlate it with our carrier movement, and we can tell you exactly the position where our carrier is during the process where we have that arcing. But you have to manage all the data flux, and you have to control it. And in the best case, we want to have it in real time during the production process, maybe even with a feedback loop and automatically syncing or re-engineering our system. That's just a screenshot. I was not quite sure on the connection. I could connect online to our server back at the institute, and we have in the meantime, I think mostly over the pandemic, the last 2 or 3 years, a lot of our equipment fed into online into a database. So we have a wet chemical cleaning line with different bases, and so I can monitor all the bases worldwide in real time. We have it for our coding system. Here's just some pressure readings, some information on the transport system where we are, and you can make that available, and you have a fast access to, like I said before, a vast number of data. The challenge is how to reduce the data and to really get the information you need for your process. And this brings us to the next step, moving towards a digital transformation. So we have a lot of tools. I have a great colleague dealing with plasma simulation. He can calculate and create nice movies like we can see here. It's always, I like it always in a presentation when something is moving and you can see it. So what you can see here, and I will go to the next slide, so it explains a little bit better. That's a simulation for a vacuum chamber just with the core elements we want to address. So this is 2 targets. We have co-sputtering of 2 materials. You can see in this case the electron density with a particle in cell Monte Carlo simulation. And from the electron density, this is the workpiece that will be coated. We get a lot of data. For example, we get the electron density, the plasma density, the energies of the different particles. And by that, for example, we can calculate the particle flux to the substrate. If we have the particle flux to the substrate, also with angular resolution, we can feed that data and even simulate our film. So we can grow a film virtually and define some of the outcome parameters without even touching and conducting an experiment. And here's a nice example. So the molecular dynamic simulation were calculated by the Laser Center Hanover within the frame of a project. And you can see the situation I've showed before. So here were the two sputtering sources, co-sputtering towards different samples. That's like a tube, so that's the facing area, and that is the tilted on the bottom line a sample. And so what you see, this coating, here's an SEM cross-section, is a dense, compact coating, and that's also what the calculation was saying. So from the plasma physics, if we have an angle in normal coating, we will expect some tilted growth. And the interesting thing is, you get, according to physics, to the tangents rule, you get a tilt depending on your situation, and the calculation shows you exactly the same. So it's a deviation within 1 degree of angle between the calculated values of the column growth and what we really can see. So we have powerful tools to just model and simulate our outcome. And we can put this together and calculate our processes and then feed it in. So here are just some examples. So that's the schematic of the chamber. In that case, it is an ion beam sputtering, and we can see the particle flux. In that case, this was tantalum absorption. You can see the flux of the gas, the xenon flux, and also what was observed, there was a dark spot in that area, and this can be deducted by the calculation due to scattering on the substrate and scattering of fast ions and fast refracted particles, and it really fits nice. And in the sample analysis, we see that we have an increase of the xenon ions exactly in that area where we get some deviation in the coating properties. So example and simulation, experiment and simulation fits nicely together, and we can combine this. Let's move from the simulation to the coding system. So on the other hand, our coding systems, and that's an example for system and then monitoring that was developed at IST. Probably if you're in your lab or in your production site, it might look something like that. So you have your computer, you have one computer with the fundamental machine control, with your SPS system. You have another computer with your optical monitoring that you add on somewhere, maybe a third one with some optical spectra and so on. You have all the different keyboards. Maybe you use some color coding with a black and a white keyboard and a monitor to not lose your correlation between the different systems, something like that. And what if you can combine everything into a single system? You have just one operating system, and all the different information is merged into one user interface and is operated at the same time. So in the background, you have the fundamental machine control, but you have your operational interface. In the best case, that's recalculating. So that's an example for an optical filter. That's recalculating during the coding your layer stack. So if by whatever reason your coating becomes too thick in an optical stack, you completely shift your specification. And you can lose valuable substrates, or you can use some powerful calculation, or you can have some lead time, recalculate. And if you can do that in real life, that's a big benefit, and we can access all those. So, and you can even go a step earlier. So you plan your batch, you plan the loading of the batch, you program your different batches. For example, you produce different optical filters with different specification. Each filter has a different specification. Then you have your samples. For example, you have a whole magazine of a sample holder, and the machine picks automatically the filter you want to have with the design you have. And for each design, if we're speaking about an optical filter, you have a high and a low refractive index material with a given thickness. So you have to prepare the layer, you have to maybe run in your cathode, you have to pre-spotter, then you start the coding, you wait for your stop signal, you finalize the coding, and you repeat that cycle unless you have several 10, several 100 layers for your filter. And then you exchange the substrate, you move to the next one, and you just walk through your production. So what we tried to do was to put everything in the same system. So the key features of the system we called MOCA, module layer, optical coding, sorry, maybe I will have the abbreviation later on. It's coding control application. So we have the material recipes. We don't have it somewhere on the computer. It's integrated in the program. For your material, you have the recipe, you have the deposition rate for the condition of your production system. And you even can feedback from your process data to the real, for example, deposition rate for the real density of your film, because that also depends on the system you're using. Then you take the materials, the different properties, you define your batch, you build up your layer stack, and you also have a run history. You learn a lot by each run, and you can feedback the data to have the best available data in your system. And you can run fully automated on the system. You can use some pick and place for carrier handling. You have the different carriers. You have different definition of your substrates, of what is there, and just pick and place, put it there, and just collect together your samples. Then you have an underlying control of the machine, just the background SPS for running everything, having the interlock, and monitoring in real life the thickness, having some deviations of the process, and to have the online control in the system. So starting, of course, you calculate your layer stack, you do a simulation, you get some pre-calculation of your filter, in that case, of your filter characteristic you want to have, and then you even can perform a virtual deposition run, what is happening during the process, what you are expecting, how the system will act and behave. In real life, we have a measurement system. Okay, I have to speed up. We can control all the data. We can have a reference measurement. And if we do so, we get all this optical data. If you build an optical filter, you lose some information in the wavelength range. So you have to exchange some monitoring glasses, and all those steps you can integrate into your process and optimize your production process. Also had some integration for things and key features. I will not go into detail. Wavelengths are ramping up in pre-spotted cleaning to the target, where you open the shutter and you run your filter, the first layer, the other layer was niobium oxide, the other one is silicon oxide. And you see some different features. You can learn a lot in real life happening there. And what's the influence between certain properties? There might be some situation here that's not exactly the theory, but the calculator can take into account. So in the end, you can model on a substrate with an accuracy we're still facing issues on how to handle all the vast amount of data that we have and how to draw the data we need. We have quite often individual solutions. We have real-time data, and we really need to merge them into an existing system. And one example for a digital twin optical counting system I've showed you. And what we are planning and what we are looking forward, and also that's cooperation where we just managed to go in the next step between Punta University and Fraunhofer, is aiming to future coding production system to really think on the level of production system and production engineering in the future will happen and how to move on with all the different tools we have available today. Thank you for your attention.
Because time is limited, so thank you for Raf for this wonderful talk. And I think from digitalization, and the digital transformation, I think this is really undergo by Fraunhofer ISD and led by Dr. Bandorf. So very precious experience sharing, but due to the limited time, I would say if he will be here today, and if there's some other times you may ask for. But so far we may have one question from you, if you have any question. Yes, please. Microphone.
Hello, I think it's a really interesting idea of bringing the digital twin idea to the coating system. But I'm really interested in, especially for the machine learning related technique using the data science related method. However, I think I've been working with the coating system for a while, and I think one of the most important feature, most important task to do is not only bringing big data, but also how to realize the importance of each physics features within the data. Then it is important to really filter out or cluster the data we have, then we can have a more meaningful machine learning patterns. I think, I think it will be interesting topic to work on.
Model driven, I think.
I take this one. I think what you're addressing is perfectly right. I probably didn't get the point or went too far. We have so much data, like you said, but we are lacking the diamond somewhere in between to just pull out the diamonds in the big pile of all the other data. And I'm not an expert in artificial intelligence, neural networks or whatever, but I believe there's a lot of good approaches that we can benefit in the future. And I just wanted to motivate that we have so much data, and we also have so much tools for simulation and modeling. But quite a lot of that is very intensive in the use of CPU power and is not fast enough for real-time calculation. So we have to match and we have to extract and reduce. And exactly, I'm looking forward for the experts that help me to speed up the process with that manner to help us to have the algorithms that are fast enough and smart enough and that we can train. And that's one of the key features to make it work.
Point. Thank you very much. This is why we get it together. You know, as algorithm is consuming CPU power, so they might not have enough time in situ to do process control, but pick up the diamond is important by some particular algorithm. So thank you for reminding. And let's thank our speaker again. So our next speaker is keynote speaker. As people might already know, Professor Jeff Lee. People call him Jeff Lee. And he is also the former chair of TACT and dedicate himself a lot in high beam, particularly for tribological coating. Let's give again a welcome warming.
Thank you. Thank you for your nice introduction. Good morning, ladies and gentlemen. It's my great honor to be here and to present some research work about the fabrication of some transition metal, including the nitride, carbide, and the oxide films using the so-called superimposed high beams. And also we combine with the plasma feedback control system. Okay, yeah, this is a collaboration work among 2 different universities. Before my talk, I would like to introduce this TACT 2023 will be held in November 12 to 15 in Taipei. Actually, this is a very famous international thin film conference, including 7 symposiums related all to the plasma and the thin film technology. Please welcome to join us. Okay, this is a very brief introduction of my center, the Center for Plasma and Thin Film Technologies. Okay, I just want to skip that because I don't have too much time. So Mingji University was established in 1963, and our research center was established in December of 2010. We have several groups, especially the R&D group, including 5 different categories, and also focus on the high beams technologies. Okay, we have a lot of international collaboration with different universities or research centers in Asia and also in Europe. There are a lot of famous visitors, and we also have a lot of international exchange students. Okay, yeah. Let me turn to the research topic of my lab. We try to do some functional coatings through the process of the high beams and also the microstructure and the mechanical properties and also the chemical compositions of the functional coatings. So it divided into the protective coatings, anti-sticking coatings, and biomedical coatings and other functional coatings. And specifically, we also work on the plasma medicine, the so-called cold plasma. Okay, this is the outline. I would like to talk about what is a high beam and the superimposed high beams, MF. And the second one is the plasma emission monitoring feedback control. And then I will talk about the titanium nitride, titanium carbide, and the titanium oxide. Okay, as we already know that the degree of the ionization of the plasma particle is relatively low for the like the DC magnetron sputtering. So the degree of ionization is around maybe less than 1% for the sputter target. So we need to do some modification of the working parameters, so which may have some defect or some residual stress, or even have some detrimental effect on the properties of the coating. So I think this is a very famous paper published in the 1999. They talk about this novel post-magnetron sputtering, which was later called high beams because it has a very high sputter material ionization of the copper up to 70%. And this is the image of this copper film on the trench. Okay, basically, we talk about the high beams. I think there are a lot of experts in the audience. You already know about this. Basically, we have a very long of time to charge the capacitor, and we have a very short on time to generate a very high energy plasma. And due to this kind of figures, we can see that we need to wait for a long time to generate this high energy, which means we will have a little bit lower deposition rate. Okay, the benefit of the high PIMS technology including a lot. For example, this paper talk about aluminum silicon nitride coating. According to the OES signal, for example, the aluminum plus, okay, in around 389 nanometer, and the other one is around 465 nanometer. It shows very high amount of the aluminum ion intensity as compared to the DC one. And also, according to this, we call the ion energy distribution function of the high pins. We did this one, titanium chromium silicon nitride coating. We can see as compared to the DC one, we have a higher energy tail as compared to the DC one. Okay, then we can summarize some benefit from high PIMS. For example, we have a much higher peak power density, higher than 500 watt per centimeter square, and also a rather high peak current density. Also have a high plasma density as compared to the DC or pulse DC one. However, we have a relatively low deposition rate as compared to one is only maybe 0.2 to 0.8, which is a disadvantage of this kind of a process. Okay, in the second part, I would like to talk about what is the feedback control. Okay, let me borrow the paper published by Andre Enders. He talked about the reactive high PIMS has certainly much greater challenges in terms of the process control than non-reactive high PIMS. For example, this refers to finding a desirable working point on the current, voltage, time characteristics, and can be affected by the partial pressure of the reactive gas and also influenced by some factors such as the target area, power density, magnetic field strength, and topology. So which means that we need to pay attention to this because we want to have a film with a good quality and also a acceptable deposition rate. We could not do this in the fully poisoned state. Okay, this is a very simple idea about the using OES to do the plasma analysis. This is a reactive gas flow, for example, nitrogen. This is in the beginning when we add more nitrogen into this. The target surface is kind of a metal mold, and then gradually into the transition mode. And when we add more nitrogen flow rate, it will be fully poisoned. So basically, we can select this transition mode to do our deposition, which means we can open some opportunities to increase deposition rate, reduce metal cost, improve film properties, and also fine-tune coating chemical compositions. This is a technique we use from process EMICOM. We have this in vacuum collimators to read out the signal of the plasma. And as we can see, the OES signal implies the poisoning of the target or the partial pressure of the reactive gas. So through this PM feedback control, we can control the partial pressure, the reactive gas flow rate, and also the stoichiometric of a thin film. Okay, so this is a very simple idea. This is the optical fiber, and when we analyze the chamber, the plasma condition inside the chamber, if we want to increase like the metal signal, maybe we can put more reactive gas into this chamber. If the signal of the target metal decrease, maybe we need to reduce amount of the reactive gas. So this is a very good tool for reactive sputtering deposition, especially for high PIMS. Okay, so let me turn to the first topic I would like to talk about titanium nitride. I would like to talk about the effect of a superimposed MF process. As we already know that the disadvantage of a high PIM technology is kind of a lower deposition rate. So we are thinking, so this company, okay, Melec from Germany, they think about maybe we can superimpose mid-frequency power into the off time of high beams on the same target. Okay, we only use one target. So you can see this is a target, titanium target here. So this is a high beams DC power, and this is MF power into also the MF generator DC power, and superimpose in one target. And we also use a DC bias to do this deposition. For this case, we select 6 different deposition methods. Later, I will tell you what is the difference about this. Okay, we select the total mid-frequency on time per cycle will be from 150 microseconds to up to 2,400 microseconds. And especially, we keep the target point ratio to be 50%. Okay, that is important because in our previous work, we found out that when we did the titanium nitride coating at the target point ratio of 50%, we can have a very good quality. So for comparison purpose, we also prepare pure high beams and a pure DC power, pure decoding by pure DC. And let me explain a little bit about the meaning of a superimposed MF, which means that in the off time of the high beams, we superimpose many MF pulses into that. So this is this one is the on time of a high beams, and this is the superimposed MF. So the 1.5 MF means okay, this is 150 microseconds for the total MF pulses, and for the one high beams on time is 100 microseconds. So you can see this is the ratio between that. Okay, in order to feedback control about this coating, we need to keep it as 50% target point ratio. So we find out this intensity titanium neutral at 453.5 nanometer, and we did this hysteresis curve, and we find out the 50% control. Then we set up the computer, and then we do the deposition. Here shows the pulsing configuration. You can see that this is mid-frequency, and this is the high beams, and also 3 MF. Okay, so you can see for the 24 MF, we have a lot of mid-frequency pulses in between. Okay, so according to the measurement of the target voltage and the current characteristic, when we use high beams, we have a pretty high peak current. And when we superimpose mid-frequency pulses into that one, the peak current will decrease a little bit. And for the MF power, it also shows some decreasing tendency. This is important because I just mentioned that we need to have a decoding titanium nitride with a titanium to nitrogen ratio to around 1:1. So in this, in these 8 coatings, you can see the nitrogen to titanium ratio is around 1, 0.98 for pure high beams, and the highest one is 1.06. But unfortunately, for the DC one, it's only 0.92, means we have a little bit lower nitrogen content. Okay, this is the X-ray analysis. We can see it's a pure titanium nitride phase. And using this X-ray to calculate the grain size, we can see the increase of the grain size when we superimpose more MF pulses. And for the DC one, it's a really large grain size as compared to others. So this is a cross-sectional morphology for each coating, and this is a DC one. So you can see it's a relatively coarse columnar grains. So this is a deposition rate, and especially the deposition ratio is very interesting. For example, for the pure high beams, it's only 1. We take it as 1. When we superimpose more MF pulses, the deposition rate increased from 1 to 1.33 and up to 2. However, the DC one is 6 times higher than the pure high beams. And for others, it looks like the increase of a deposition rate is limited to around 2.16. However, the harness shows quite different behaviors. Later, I will talk about this. This is the hardness. As we can see, when we superimpose from 1 mf, 1.5 mf to 6 mf, we have a pretty high hardness, around 30 gigapascal. But when we superimpose more mf into that one, the hardness will decrease to around 25, but which is also, but still much better than the DC one, which is at 16. For the electrical properties of the coating, we also can see that for those coatings fabricated by the pure high beams or superimposed high beams, the electrical resistivity is around less than 50 microohm per centimeter. But for the DC one, due to its rough or large columnar grains, it shows a pretty high electrical resistivity. Okay, this is a short summary of this talk in the first part. When we superimpose 6 mF pulses into that one, we can have a 2 times higher deposition rate and keep this around the same hardness and also a good, very low electrical resistivity. Okay, let me turn to the second part of the biocompatible titanium carbide coatings. We fabricate 4 kinds of titanium carbide coatings by adjust the target poison ratio from 80%, 85%, 90%, and 95%. Okay, so this is the target voltage current characteristic, and we can see that for the high beams one, this peak current increase a little bit when we have a higher target poison ratio. And here we also can see the peak power density also increase with increasing target poison ratio. And for this MF power, it looks very similar, not very large deviation. For the chemical composition, as we can see, when we increase the target poison ratio from 80% to 95%, the carbon content increased from around 70.6 atomic percent to around 80.1, which means that the ratio between titanium and the carbon decreased from 0.38 to 0.21. Here shows the cross-sectional morphology. We can see very, very dense microstructure can be seen for each coating. And especially for the deposition rate, it's a little surprising that the deposition rate just decreased a little bit when we have this 80% target poison ratio to 95%. All right, so the number is pretty high, around 17 nanometer per minute. The lowest one is around 15.4 nanometer per minute. And according to the TM analysis and the SAED analysis, for the TIC 80 coating, actually this is titanium carbide coating. But when we increase more nitrogen into that, the crystalline structure of a TIC was changed into amorphous-like. So we can call this kind as a hydrogenated amorphous titanium carbide coating. And also for the TI-95, it's also amorphous structure. And the hardness also shows a decreasing tendency. When we have a higher carbon content, the hardness decreased from around 17.4 to 14.6. And because this is kind of a biocompatibility evaluation, so we did the MTT assay using MG63 cells and the HACA-T cells, which is the skin cell. So for the comparison, we select TIC 80 and the TIC 90, these 2 coating, and also the 316L stainless steel, which is a very commercial compatible and the biomaterials in the real application. So for the MG63 cells, this is day 1, 3, 5. And as we can see, for the green and the blue one, those 2 coatings shows much better biocompatibility than the 316L based on the MG63 cell. And for the HACA-T cells, we also have a similar result, which means that these two coatings shows much better biocompatibility than the commercial 316L stainless steel. And especially for this TIC90 coating, which shows much better than the TIC80 for the crystalline one. The amorphous one looks better than that one. Okay, in order to do more evaluation of this wound healing or migration assay was used. This is a kind of a kit. We can use this kit to separate the cell, and then we stay for 1 day and to see the migration of the cell into the center part. So this is kind of a very popular method to estimate the surface biocompatibility for the cell. So we use HACA-T cells to do this. Okay, this is a blank for 0 hour and 24 hours. There are around 29% remaining area, which means that there are 29% left without any cell migration. And this is a stainless 316L. So we can see this is around 23% remaining area. For the titanium carbide 80% coating, we have around 14% remaining area. And for the TIC90, it looks pretty good, almost 0%. So this is a very interesting result, implying that when we use this kind of a hydrogenated amorphous titanium carbide coating, it shows pretty good biocompatibility than this nanocrystalline one. Actually, this is also proved by other research groups in the world. And in order to evaluate the in vivo behavior, those two, the MTT assay or the migration assay was an in vitro one. So we did this in vivo evaluation. We did the subcutaneous implantation, okay, including 316L and the TIC90 and TIC80, and this is a blank. So we select 3 samples for each SD rat, and 9 SD rats in total implanted for 5 and 12 weeks. Okay, this is after 5 weeks and 12 weeks, and we did the histologic image and to see is there any inflammation after this kind of animal test. And we can see that according to these images, there's no any inflammation reaction occur after this implantation, which means actually, as we already know, 316L is a commercial biomaterials and already applied in the real application. So which means that for these two coatings, when we deposit on the 316L substrate, we also shows pretty good in vivo results. So this is a short summary of the second part of the titanium carbide coating. Basically, according to the TM analysis and also from the migration cell migration test, we can see very good biocompatibility was attained from these two coatings, and especially for this hydrogenated amorphous titanium carbide coating, it shows pretty good in vitro and in vivo result. Okay, let me turn to the last part of my talk, the antimicrobial and the transparent titanium dioxide coatings. Actually, we already published these 2 papers in the last year. Okay, as we already know, titanium dioxide is a very famous photocatalysis material. Basically, when this titanium dioxide surface is illuminated by the UV light energy, which is equal or higher than the band gap energy of a titanium dioxide, the excitation of an electron from the valence band to the conduction band occurs, and a positive hole is thus created in valence band. the chemical species observed on the titanium dioxide surface will have the redox reaction with this photo energy generated conduction band electron and valence band holes in the excited state. The activated titanium dioxide materials thus induce strong oxidizing reactions and generates active oxygen species to decompose various microorganisms or organic compound to destroy the outer member of the E. coli cell and also kill the bacteria. So I think that is a very popular, and a lot of people already did a lot of research about this kind of a material. And in this work, we like to know the effect of the target point ratio on the fabrication of the titanium oxide films. So we adjust, okay, we have a, for example, we have six coatings with a different target point ratio from 10 to 90%. And the last two was fabricated on the glass substrate to do the transparency measurement. Okay, I still have 5 minutes, right? Good. Pretty good control, actually. We use a hysteresis curve, as I already mentioned that. So this is a hysteresis curve, and this is OES signal. We use this wavelength to do the feedback control. And this is the target voltage current characteristic. So we add 18 MF pulses in between. Also, we can see the peak power density increase with increasing target pointing ratio. According to the X-ray analysis, we can see that when we have only 10% of a target pointing ratio, we can produce pure TiO phase. Okay, well, where is that? Okay, this one. Okay, this is a TiO. Okay, here, TiO. When we add more oxygen into that, like a TB30 or TB50, it changes into anatase phase. And for the TB80 or TB90, we can see they are mainly anatase microstructure and with a small amount of a rutile. According to this equation, we would like to calculate the anatase fraction in two phases mixture. So according to these four coatings, the anatase fraction is around from 42% to around 89%. And specifically, we take a look about this 004 plane. You can see the intensity of the 004 plane increase when we have a higher target pointing ratio. So we calculate the anatase 004, the intensity of 004 to 101 ratio. So you can see this is a rather high increase from 0 to 0.64. Later, I will talk about why we will take a look about this. And this is a cross-sectional morphology. As we can see, when we add more oxygen into this, we have a lower deposition rate. That is very typical. And this is a surface morphology. As we can see, very dense and low surface roughness morphologies. And according to the TM analysis, the TB50, it contains anatase phase and the rutile phase together. So the grain size is really, really narrow. It's around 53 nanometer in the average. And this is a TB80. So you can see also include the anatase phase and some rutile phase. The columnar grains is around 69 nanometer. And this is a TB90. Okay, we can see these are mainly anatase with some rutile phase. And these are the cross-sectional dark field image. We can see those grains are, the width of the columnar grains is around 73.8 nanometer. Okay, and after this, we did the scratch test to evaluate the adhesion of the coating. You can see for the TB80 and the TB90, it shows actually pretty good result. For the LC2, it's a 22.3 Newton. As compared to others, it looks much better. And especially for the TB90, so we add a higher load to do this. So the critical load around 46.4 Newton. This is the antimicrobial test against E. coli. So we use TB50 to TB90 to do this antimicrobial test. The annotated fraction also listed here, and the ratio of the annotated 114 to 101 ratio is also listed here. So let me explain a little bit about this. The titanium dioxide film with dominant annotated 001 family plane high energy phases have a greater effect on the surface separation and transfer of photo-generated electron-hole pairs, resulting in a significant improvement of the quantum efficiency of a surface-mediated photocatalytic redox reaction. So as we can see, this is the control. You can see that when we have a higher amount of 004 peak, the antimicrobial test is 100%. Okay, we got a very good quality of this coating for the antimicrobial test. And finally, we take a look about the transmittance. So this red line is a TB80, and the black line is a TB90. So the average transmittance goes up to around 81%. Okay, so this is a short summary of this, the third part. So we got some nice process parameter for the high beams MF superimposed one, including here. So we can have a very good annotated ridge phase and the 100% antimicrobial ability and the higher than 80% transmittance. So, okay, let me conclude that. I think the last part is very important. This work opens an opportunity for the fabrication of a transition metal nitride, carbide, and oxide films by reactive superimposed high beam MF technique and plasma emission monitoring feedback control. And thank you for your attention. Thank you.
Thank you very much, Jeff, for this wonderful and nicely organized outcome. And then maybe just one question. We might have 10 minutes left behind the schedule. So maybe just one question. Do we have any questions? Yes, please.
A very nice talk, Professor Lee. I'm very interested about the transition metal nitride and carbide. And I know the titanium nitride and carbide can have a very wonderful application, especially for the bio application. I'm wondering if any, can you do any other transition metals like maybe molybdenum nitride or tungsten nitride or carbide for other applications? Yeah, thank you.
Yeah, sure. Actually, we did publish some paper regarding the chromium carbide, chromium nitride, and also some tungsten carbide, tungsten nitride, tungsten oxide. Yeah, sure, it's no problem. Yeah, using this kind of feedback control, it will be well controlled. Yeah.
Yeah, I think those can, if you can deposit those materials, it can be used for other optical electrical device,
Yeah,
and that's
that's
very, that will be very interesting too.
Yeah, thank you.
Thank you, thank
Sure,
you.
Sure, thank you.
Yeah, yeah. I was working on two-dimensional transition metal sulfide and nitride for optical device. So I was thinking how I know it's like a micron thickness, but I also can see can you control like a monolayer deposition? I think this will be a challenge, but I think that will be the future work as well.
Yeah.
Yeah. Thank you.
Yeah, actually, in our lab, we did some coating around 100 nanometer thick, like titanium dioxide or tungsten oxide. Yeah, it works, but I'm not quite sure about maybe down to 10 nanometer. I don't know about that, but it should be okay, right? I don't know. Yeah, sure. Actually, we did some the corneal oxide applied in the semiconductor circuit. The thickness only 10 nanometer. Yeah, I remember that. About 7 years ago, we did that. It works well. Yeah.
Yeah, maybe I will ask you more questions after
Sure.
the talk. Thank you so much. Thank you.
Yeah, thank you.
And also one address is that without the chemical, we wouldn't be able to create a different degree of target.
Yeah, sure, sure. That's right. It works very well. That's right.
Again, thanks our speaker again.
Let's take a break until 10 to 11. We have prepared food and beverage outside of this meeting room. The coffee break is sponsored by Plazas. Please enjoy. The next session until begin at 10 to 11. Please come back in time. Thank you for your cooperation.
也请大家移驾到那个展示摊位哈 ，exhibition booth， 我们可以在那边。摊位展示大概是讨论的蛮踊跃的，所以舍不得进来。OK。亲爱的来宾，请赶快入座，我们下一场马上开始。
The section is about to begin. Please take your seats in the conference room. Thank you.
Thank 我们亲爱的来宾还没有坐定之前哈，大家可以先看一下这个标题 Reactive High Beams。那个反应性渐度的话呢，其实发展很久，但是 High Beam 啊，它在反应模式的时候，它有很多的不同之处啊，所以呼应一下我们第一位 speaker 那个 Dr. Rob Bendoff 啊，他在这个做 control 啊，他在这个做智能化的这一个场次里面提示的，还有我们第二位 speaker， 那个李志伟理事长他所提到，他所用到的这个技术，发展了不少这个材料来做应用。那所以接着这一场的话呢，就会是在从 control 的角度来跟大家分享。So I think it's about time for us to begin the next session, and this session is with topic process development of reactive high beams. As I explained that high beams, when combined with reactive technique, you will then be able to develop a lot more ceramic compound coatings for different applications. So echoing our first speaker, talk about smart control of the PVD process, and our second speaker about the application of using reactive control. And then now let's go back a little bit to the the side of control for reactive high beams. So Mr. Stefan Corner, who has a lot of experience in coating, particularly in the reactive coatings. So, and he is also from Fraunhofer IST. So let's give him a warm welcome.
Thank you. Yeah, great pleasure to be here. So today I want to show you some insights to the process development in reactive high beams. And it will not start. Also, okay. Okay, great. Yes, we skipped it. You have it there. So what is the outline? So I want to motivate a little bit what high beams is. Then we go over to reactive sputtering in short. Then we come to reactive high beams, that we have a basement how to get the control of this. And in the end, we want to show to some control schemes of the reactive high beams. For the beginning, I want to motivate with a small, short video what high beams is. So some people who maybe don't see any high beams process. So
high power impulse magnetron sputtering is the most recent development in highly ionized pulse plasmas and is currently in the transition to industrial production. While conventional DC sputtering uses a constant power level, with high beams the power is delivered in short pulses, with peak power levels some orders of magnitude higher, but with comparable average power. This results in modified film properties, such as higher density, higher refractive index, a modified crystalline structure, or modified hardness of the deposited films. For complex surfaces, significant improvements can be achieved in covering surfaces, which are not parallel to the sputtering target. Some industrial high beams processes already exist today, while a significant number is under development.
okay, so a little motivation video. So we can see here, as also shown before, that some underlining. Yeah, come on. Okay, great. Okay. Yeah, most of you know this DC process. So we have a duty cycle, and then you can say, okay, we have 100%, and then you try to modulate the pulse, and then you can increase your power peak density to your target. But here somewhere you have the power limit, or you melt your target. So sputtering is a very high energy process, so you can also melt your target and destroy some processes. So we go down here, and so we can have a peak power density increasing with high beams. That's what you have. But our usage here have to be reduced. You see it also here from a normal DC to the, let's say, smaller module power up to the small high energy peaks. We have normally not only metal layers, we also have compound layers. So only in few cases, we have some metallic coatings for mirrors, silver, something like this. Most of the compounds are today more like oxide, nitrides, carbides, we've seen also before. And here's some of this material compound layers. So if we have oxides, typical aluminum oxide or silicon oxide, niob oxide, and also nitrides. Titanium nitride was also shown before, and also carbides, mostly for friction and hard coatings. And so we used reactive sputtering to have metallic targets and reactive atmosphere to get, let's say, cheaper materials for the same material we have deposited. Most of you know this, but you can say, if I have a reactive gas flow and look to different parts of the process, we see if we increase the reactive gas flow, we have this typical shape here in the reactive gas pressure, oxygen, nitrogen, for example. And we see that we mostly have this hysteresis behavior. Also the cutoff voltage decrease or increase depending on the material. And also the deposition rate decrease if we have this typical compound mode on the surface of the target. So we can take some material properties that are given. So we can say this hysteresis makes the process very complex and very hard to control. And this hysteresis should be avoided in the best case or get narrow, that we have a smaller window to control. And on the material side, we can say that we can use a special material. For example, if we have the sputter yields of the metal and the compound mode, and it's to 1, then this typical hysteresis or transition mode shape here, like S, can be nearly 0. So we have no hysteresis. We also have this material component. We cannot change this. The sticking coefficient, that you also have a low sticking coefficient. Then you have also a good shape to control. If you have a high sticking coefficient, aluminum oxide, for example, then you have this very strong transition curve. What we can do for process design, so also machine production, can make there some, let's say, engineering to, for example, take higher pumps. So if we increase the pumping power, then we can also decrease the shape of this S transition curve with very high pumping speed, and we also can avoid this. But this is very expensive, and you don't have even the space for such amount of pumps. Also, if you have a small target size into the volume, you also have a less shape of this curve. So if you have very small target and a very high machine volume, then you also have nearly no hysteresis or a smaller hysteresis. But if you upscale it to industry style, then you often are faced with this problem. If you have a laboratory with a small batch coater and small targets, then it's somewhere between here. Okay, then we come to reactive sputtering. To motivate this a little bit, for example, for zirconia, we can say, okay, normally if you have the DC process here, then you have the normalized deposition rate. Then you say, okay, if I increase the oxygen flow, I have firstly the metal mode, and then and somewhere here we are in the compound mode, and then we have a small deposition rate. If we now use reactive sputtering, it has been shown that it can be possible that we have in a starting point a less deposition rate if we have no oxygen, but if we increase the oxygen, then we have a juicy point where we say, okay, we have here on this part, for example, a higher deposition rate because this DC switch here, switch on off. And then we can say, okay, here we have a higher deposition rate by high pumps, reactive high pumps, if you have, for example, this T on to T off time. But if we have to change the pulse moduli, then we have here a decreased deposition rate. So here we have maybe better properties, but a less deposition rate. So here we have to say exactly which kind of pulse parameters we have to affect or address, that we have somewhere maybe this point where we are better with reactive high pumps than the reactive DC. And this motivates also to control, because we want to stay in this point because we don't want to fall down in this curve. Now, a little bit more complex. If we could look in the process, here we have the target, here we have the substrate, and here somewhere is our plasma between. And we can say, okay, to carry the current, we have our primary current by the ions. They are attracted to the target, then they get deionized, and then they come back, we ionize, and then we have this typical process gas recycling. So, this is a normal case of a DC sputtering. If we go to reactive hype sims, we also have target atoms. They normally go to the substrate, but now we have more energy in the process, so we have also ions. And these ions can be attracted by the electric field, that they also come back to the target. And so we have a second sputter recycling process of the matter. And we have, so both circuits that we say, okay, we have also process gas and self-sputtering. Yeah, if you look here to reactive high pumps, we see that's the metal mode and the poisoned mode. And we see that if we compare which part of this current is the major part of the whole current, we see that we have one time here the gas recycled, then we have the normally poison mode with this triangle shape here. And if you have metal mode, we have more this typical saturated mode. We also can show it here, for example, if we have a typical current over time from a titanium target, we see that the voltage will increase. We have this typical saturation effect here. And if we take this 1100 volt from the charge, we also can do this with adding some oxygen inside, in our case here 1 to 12 SCCM, and then over time we see that this shape changes. So the peak current change with process gas. Okay, how many time we have? 3 minutes or something? 4 minutes, okay. So we skip this here. Okay, it's too much for 4 minutes. Yeah. Okay, this is a juicy point also here shown. We later can talk it in the lunch. Most important is this slide here. If we want to control reactive sputtering, we have our process here. We have a process control unit, and we can say we can look to the discharge power, the pulse modes, reactive gas flow, and then we can look inside the process by different sensors like partial pressure or target voltage, OES, and so on and so on. And then we have to get this loop to control the whole process. And these are our eyes, let's say, and also here. And then we need an intelligent unit, we see data science and so on. That this here is a lot of brain work, that we have the stable process to control. And this is maybe reactive sputtering. You see, oh, okay, we have here some parts, partial pressure controlling and so on. Then we go to reactive high pumps. Then we add some new dimension with also the pulse modi. And newer ones, we have also this pulse length for positive pulse or bipolar. And then you have delay, how much ever. So it's become more and more complex and you want to control it. So you need a very, very good process control unit to use this. And for this, we have reactive high pumps. We can also process, look into the process by mass spectrometer. This one is the most expensive version, and so not often used, but give you a good sign which species you are in the process. You have typically the lambda probe to look to the oxygen. This is very common and very cheap, let's say, but you are fixed only on to oxygen, no nitrogen. Then we have this OES spectroscopy. So I've seen before, and also in the later session, you get more insight in this part. It's a very nice tool to see the fingerprint of every species here, and then you can control to the emission lines. And you can also look to the peak current, as shown before. The peak current is very sensitive to the process parameters, but it's also good fast feedback control, and you can also control over this peak current. Here, Mr. Shimizu also showed something to say, okay, we have here as the reactive gas flow, or we take the frequency and we see the shape of this peak current is can be changed, but it's very hard to control. some examples. For example, if you have partial pressure, you can also go down here with partial pressure and go from the frequency or off time. You can do it for different oxygen partial pressures. You can take titanium oxide and can see, oh, my lines are very affected by this. You can also go partial pressure of zinc aluminum oxide. And you see this is a DC process, and our resistivity is increased if we take the reactive high pimps. We can also do this for solar cells. We skip this here. We can also, as shown before, a mixture of MF and high pimps. And in the end, we can say, okay, we can also do aluminum oxide from the double rotatory cathode and have a nice breakdown field strength of 78 voltage. And we come to summary. We say, okay, most coatings are compounds, so it's good to make reactive sputtering. It's because it's the cheapest cost-effective solution. We have reactive high pimps, which offers workly similar, even higher deposition rates. If you have a juicy point, we have improved properties, trench filling, harder coatings. We have industrial scales, and now we get also advanced process monitoring and control, shown by Mr. Bahnhof before, and also commercial solutions available. So we are ready for industrial reactive high pimps. So thank you for your attention.
Very important sentence at your last slide.
Yes,
we are ready.
it's the most important for today.
We are ready. That explains why we have so many delegates from industry.
Yes.
So don't disappoint them.
Yeah.
I'm joking. Yeah, yes. Okay. Thank you for this nice talk, and going back for nourishing about the fundamental of reactive high beam sputtering and the control. And so just one question. Yes, Professor Kai.
I like to ask the role of oxygen. You
Yeah.
introduce oxygen gas, and
Yeah.
then so discharge current increases.
Yeah.
That is different from what I expected. You introduce oxygen, then negative ion, negative O minus or O2 minus produced. Negative ion, many negative ion produced.
Yes.
Then so usually then electron density is going down. Yeah. If the plasma density is constant, many negative ion produced, then so electron density going down.
Yes.
Then
Yes.
so discharge current should be going down.
Yes.
But
Yeah.
Then,
Yes.
what kind of did you use power supply? You're using the constant voltage power supply?
Power supply.
Power?
We have constant power.
A constant power.
Yeah. And then we increase the peak current and have free float peak current, let's say. But you can track on the points, go into peak power or even partial pressure and so on. But we looked also to the process in a moment. Von L?
Yes, please.
So the point is what you're mentioning, we are measuring at the power supply. And you're shifting when you're going to the reactive process to a poison target surface. And you're changing the secondary electron emission coefficient. And you're changing, like you said, the plasma properties. And that in the end results in the change of the signal and the ionization. You're right that we are producing the negative oxygen, but we hardly see the negative oxygen in the reactive sputtering. It's 5 to 10% of the negative oxygen or of the reactive gas that's really in front of the target. Most of the reactions take place at the walls and on the substrate, and the process is mainly influenced by the change in the secondary electron emission by the compound formation of the target, and that will result for the power supply in the change. And you have to run, and usually you have a big capacitor at a certain voltage level, and this drives the current shape. And that's a general feature regardless of the power supply where you're running. It's a little bit on the operation mode, but it's mainly just the physics and the power supply. Yes. But you're perfectly right, the negative oxygen, the charges are somewhere else where we collect them, therefore we don't see the decrease but the increase.
Okay, thank you. Rufus supplement. Yes, and my own laboratory experimental work is, the observation is the same. The peak current, when oxygen increase, peak current increase. And I think as supplement by Ralph is because of the target surface effect, because secondary ion electron emission is higher. Yeah, so to make a target current higher. Okay, so thanks our speaker again. So let's move our eyesight a bit shift towards the application. So our next speaker from MIRDC, Tony Cho, Dr. Tony Cho, will share us about the application towards high entropy alloy, which is hot these years because you get high entropy alloy in thin film form. We'll have a lot, particularly for tool coating, for decorative coating, and a lot of variety of coatings for application. So let's give our speaker a warm welcome.
Good morning. Very honored to be invited in this forum. But I think a long time why Professor He will invite me. The one solution is we know each other over 30 years. Okay. About this talk, application of high entropy alloy coating on cutting tool, I will call this section will be a soft talk. So everyone, you can relax and sit back. I will talking in from industrial application, the point of view. Okay. During this formula and after that, if you have technique exchange, please don't hesitate to contact me. This talk about the content about the first, I would like to introduce. I'm from MIRDC, and Dr. Randolph had visited us several years ago. Great to meet you. Yes. Okay. MIRDC established in 1963 and funded by United Nations Special Fund and the Ministry of Economic Affairs. Last section, the Minzu Daxue, also established in 1963, the same years. Very interesting. And MIRDC is the third biggest research center in Taiwan. And we have the employee about 990 people, and the yearly revenue about 130 million US dollars. Our headquarters in the south of Taiwan, Kaohsiung. Now, this place is Taichung. So, MIRDC have the regional department around Taiwan, so we can provide very close support to our local industry. We are trying to promote international cooperation. Like this slide, you can see the Germany, the IST, and France, the ECM group, and the USA, the Georgia Tech, and Japan, the AST. So we are very eagerly to cooperation with the local university and the overseas institution. In the MIRDC, we are focused on 5 areas. I will talk about this. This is a high value added precision micro manufacture. And this part is our topic I will talk in this morning. And another area, we are focused on metal material and the medical device and the healthcare. And another is high value equipment, and another one is the green energy. Okay, I'm from the service coating and the heat treatment section. So we have established technology and on established or we established. Or you can see this today's the talk I will talking about the coating for harsh environment for we call it the high entropy alloy. Another core technology is heat treatment technology. Just we know if your heat treatment is not good enough, your coating on the substrate that you can provide your life or you enhance the property. So your heat treatment technology is very important. So our section we have in the same time we have do some research. Okay, we earned the R&D 100 award on 2021 about the thermal heat treatment technology for the micro or small part. Or that's the 20 and the 21. This small part is very important because use many transmission gearbox. Or that's very large in this area. And the last year, we also won the 100 the award 20 and the 22 for the gases process for low temperature surface hardening for 3 series stainless steel. The low temperature means less than 500 degrees centigrade. This is very popular and very in the harsh environment, like the fluid machinery and the valve part and cutting tool, just like. Okay, this is our section, our equipment, and our research topic. We can all design by ourselves and to provide our local industrial need. So we can have many the batch type sputter system and the roll-to-roll sputter system. And the E-beam evaporator is from Urbach, Japan. And the hybrid coating and the barrel coating. This is in our lab. We can have a variety of the coating system. High pin system in MIRDC, we the arrangement of power supply just like this. We have one set of ion source, just like this, and the 3 sets of DC power supply, and the 2 sets of high pins power supply. And our dimension of coater is about 600 plus the 500 millimeter. Okay, the Professor Ye proposed the high entropy alloy in 2004. The high entropy alloy have the co-effect we call the thermodynamic and the kinemic. And another one is the structure because they have very shear lattice distortion. And another is the cocktail effect. Because this co-effect, they are very good when you use in high temperature and in harsh environment. From the industrial point of view, the coating is not the bottleneck of the high entropy alloy, because the high entropy alloy, they are not easy to cast, not easy to roll in. So you have to make a good the target for the afterward the coating. So from our experience, the bottleneck of the high entropy alloy coating is how to make the powder, the atomization of these 5 elements, the high entropy alloy coating the powder. That's the bottleneck. After that, the first one you must to how to solve the melting problem and the atomization. And after that, hot press to make a target for sputtering or arc process. And after that, the coating is in this formula, we are talking and discuss the detail. So from our experience, the vacuum induction melting inert gas atomization is the suitable way to solve the powder problem. All these the system we established in MIRDC already. Okay, this is the melting and the pouring during the VGAP process, and after melting, and we will atomization to produce the powder, and the powder. The most important is how to control the chemical composition of the particle and the particle size distribution. I think that's the important how to break through the application for the high entropy alloy. Okay, this slide shows the S-event mapping analysis. After the powder had made, and we are trying to hot press this target, and we can see this is the particle size about 60 micron. And from mapping, these are different alloy: aluminum, silicon, chrome, titanium, and the niobium. From the mapping, we can control each element composition at the 0.2 and 4.8%. The variation of each element composition. Traditional casting, not easy to make so big the dimension, the target. The powder way is more feasible to produce that scale, the target. Okay, from the industry application, we just not to solve the material problem. Another issue is how to provide our local industry, how to have the good design for your source. This is the traditional design, and we are improve the spot source design. Traditional use the one-piece alumina, and we try to enhance the strength and avoid the alumina corrosion problem. We are changing to the composite, the concept. And another one, the high entropy alloy, very poor thermal conductivity. So you need to improve the cooling system for the sputter source. So we had done many the improvement design, so we can decrease about 10 degrees in our new the cooling system. And another one is we can not use just the fixed magnetic field, and we use the adjustable magnetic field. Thus, you can increase the target utility from 35 to over the 40. Okay, from the application, if the material not suitable, chose in the long term, the immersion in water, your your source will be corrosion, very serious, and you have to rework. Renovation this will take many time and cost. So we design the composite material to enhance the the target, the lifetime. Okay. This high entropy alloy, aluminum, chrome, nitrogen, silicon, titanium, this coating, like we obtain the hardness over the 34 gigapascal. And another one is the water contact angle, larger than the 98 degrees. And the oxidation, high temperature, over 1,000 degrees. And another one, adhesion, were higher than the 60 Newton. This property is very good for the application for the cutting and for the molding. Just not only the hardness, the water contact angle is very important issue for the anti-sticking application, like IC molding industry. Okay, this is some application. There are two system high entropy alloy. The first one is we can use in the cutting tool for the composite material. And for high-speed forming die for screw parts. We have done the modulation in different fields about the aerospace and the PCB board industrial and the bicycle part. And we have do some the comparison, just like life is hands. And we call it the performance and the cost improvement. After coating, you will increase your cost. But the most important, how to compare the performance and the cost, the ratio. Right? At least they were about 30% improvement in different fields. In Taiwan, the IC package is a very, very important industry. The output of per year over 3.8 billion US dollars. And the important issue is how to solve the sticking issue when you are doing some the package. This is during IC packages, they were sticking on the mold. They will damage the IC. So we are use the high entropy alloy coating to reduce the adhesion force between the molding and the compound. This is the life improvement of production life. They are over 50% the production life enhanced. This is traditional use of the electroplating hot chrome, and we use the high entropy alloy nitride to improve the lifetime. This is a micro drill. In the PCB board, the micro drill, traditional, they were, when after the 2000 drilling, they need to rework. So when we done some the high entropy coating on the micro drill, we can extend it at least 3 times. Traditional, the 2000 times, this micro drill need to rework. But after we are coating on the micro drill, they will extend 3 times at least. Okay, another one is the glass molding. This is very important for the automobile and the projector because the glass have the very good the optical property and the weather resistance property. The issue of the production is that there were sticking problem between the glass and your substrate. So your mold surface needed to coating some the protection the coating for avoid the glass sticking on your mold. Okay, this is we can compare. This is the before thermal cycling and after thermal cycling. They have also maintained his FCC solid solution. So it means in over the 750 degrees centigrade, they can keep the phase very stable. Also, that can provide very good the high temperature the performance. Okay, this is the conclusion. The high entropy alloy have the characteristic can provide very good high temperature and high hardness. So it's suitable for cutting tool and the mold in harsh environment. And from the industrial application, the main limit of the high entropy alloy is the quality control of the high entropy alloy powder. And we found the VGA process can effectively control the quality of the powder. Okay, the last is our acknowledged. Thank you. Thank you. Thank you, Lindsley. Thank you.
Thank you for our speaker. I believe that you have already touched a piece of high entropy alloy. You know, a long time ago, a mobile phone company claimed themselves to have to develop the high entropy alloy for their mobile phone case, but eventually it's not still on the market. Only a piece of injection plate for extraction out of SIM card. You know what I'm saying? And you also know how difficult it is to develop high entropy alloy for application. So the difficulty, as claimed by Tony, you know, they choose it, atomization of the high entropy alloy, the most difficult part of the coating journey, starting from the beginning. So it remind me the former US President Kennedy. We choose to go to the moon not because it's easy, it's really difficult, so we go there. So thank you for developing. So next time, are you ready for shipping your high entropy alloy target?
Yes.
Okay,
yes,
great.
It's already.
Okay, thank you so much. And we all take this advantage from the efforts made by MRDC. So just one question. Is there any question? Yes, please. Oh, okay. All right.
When you mentioned preparing the targets, that was mainly a hot isostatic press in the beginning. Do you have a chance to have a molten target, a metallurgical mixture of the target? Because with the hot isostatic press, you have the mixture of the different phases, and sometimes you want to avoid the mixture or the demixing of elements.
Yes. From our experience, we use the Procast the software to calculate the different alloy the composition, and you can predict what's the phase ratio. That's important. If you use traditional way to try and analysis, that's not good enough. Just like the Bendorf you talk, the digital transformation. During the powder the manufacture, we also need the digital the way to quickly to find the suitable the alloy ratio. That's important because during your test, where the cost very much, you need use the digital the software to simulation. I think that's also important for the material manufacturer. Thank you.
Thanks for your nice presentation. I just curious about the oxygen content of your target. Is that a big issue or is not a problem at all? Thank you.
Okay. The oxygen, the content, that's depending on during your melting, because our system, melting in the vacuum. So the oxygen, the problem we can control to very low the limit. So you need to in the vacuum to melting and vaporization. That's important. Yes, thank you.
Okay, let's thank our speaker again. Now our next speaker, from the beginning to this moment, it's all talking about something hard. And our next speaker will talk about something soft by using high beams. So let's, this talk is also the research outcome of this DETW project. Let's give Dr. Chef a warm welcome.
Okay, thanks for the introduction. And I am Ping Yan from the Institute of Plasma in Fengyang University. I glad to have the opportunity to share some outcome in the DETW project. And based on the DETW scheme, the Institute of Plasma side would like to develop some high pins application and the process. So the title that I want to present is a high pins copper layer on the flexible substrate for a conformer for electromagnetic shielding purpose. Okay, so in the beginning, I would like to introduce the demand for the conformal electromagnetic interference EMI shielding film, and why we choose high pins to deposit the copper film. And then I also want to show some outcome of the high pins application in the Institute of Plasma IOP, and what we have done in this research. And finally, I will give a conclusion. So here is the number of the EMI shielding market. The EMI shielding market. So the increase in the higher density for the semiconductor package and the electromagnetic pollution, especially for the high-speed electronics and the high-frequency communication, and the IoT and the tightening regulation will push the EMI shielding market. So in order to solve the electromagnetic pollution, the EMI shielding material will need and with some feature such as the broad absorption of frequency and the low cost and the fierce reliability and the high stability and the light and the thin and the easy possibility for fulfilling the various application. And till now the EMI shielding mechanism is widely discussed, and I will summarize here. So among them, the reflection is the most important factor for the metal for providing the EMI shielding property. And then we can also use the dB to quantify the shielding efficiency of the material. So as compared to the traditional compartment type shielding, a compartment shielding material, the conformal type of the package label shielding by using a conductive film to integrate it into the package is widely used now because the advantage of the small size and the lightweight. Here. Okay, so here is one example in the iPhone. So we can see I can see the conformal EMI shielding film is now can be applied in the front end module, the two front end module and one Wi-Fi module. So here is the commercial product of the conformal EMI shielding production. Okay, so and then and the market of and the company that the Tatsuta is the a major player. So here is the configuration of the Tatsuta product. So we can find the shielding there is around 100 nanometer, and then the shielding film is prepared by using the evaporation of the silver. So here we want to propose using the hypings process to deposit the copper film for the conformal ENI shielding film purpose. So why we choose the hypings process is now that during the hyping deposition, a very high power density will input a very short pulse, and then to generate a high degradation of the ionization of the Spartan species and the high rate of the molecular gas dissociation to form a very high density plasma. Therefore, by taking the advantage of a high density plasma, the hypings can enable to deposit a well adhered coating with the desirable property at a relatively low depletion temperature. So the instilled plasma has spent much effort on the hypings for many years. So here is the R&D roadmap based on the substrate temperature and the peak power. And currently we have successfully synthesis of the copy coating and some tool coating, decorative coating, and the bio-related coating for the various application. And based on the advantage of the high fin adhesion and the low depletion temperature, the hypings can also used to deposit some reliable and functional coating on the flexible substrate, even the stretchable substrate. So we believe the hypings is recognized as the best platform to deposit the carbon film on the PU foil for the conformal EMI shielding purpose. And then as compared with the commercial product, the benchmark for this work is the film thickness should be lower than 200 nanometer to prevent the stiffness, and the shear resistance should be lower than 2 ohm per square, and the EMI SE and the EMI SE value should be higher than 55 dB. So here is the hyping system used in the study, and the typical IV curve are also shown here. So in the study, the substrate is composed of a very thin PU foil, about 25 micrometer, and a PET transfer foil. And then the hyping copper film will deposit on the PU foil site, and then after the hyping copper film deposition, and the PET transfer foil will be removed for the measurement and the practical use. So in the study, the effect of the peak current and the deposition time of the hyping copper film was investigated. Okay, so now we go to the relay and the discussion of firstly, it's known that the PU is a thermoplastic material, so the TG is quite very low. It's close to 0 degrees C. So after the hyping carbon film deposition, onto the thermal effect will transfer from the plasma to the substrate. So we can see the sample surface will be a little deformation and the wrinkle. Yes, and however, according to the SRD results, we can find the PU peak can be detected for all the sample. So it means the thermal history did not damage the chemical bonding of the PU during the high-pitch copper film deposition. In addition, with the increase in the peak current, the crystallinity of the copper film is also increased. And here is the effect of the deposition time. So the similar result of the microstructure observation can also be found here. And in addition, with increased the deposition time, the crystallinity of at the peak of the copper can also be detected, even the deposition time is very shorter than 3 minutes. So it is known that the high electrical conductivity is very important for the EMISE performance. So here is the summary of the field thickness and the shear resistance and the resistivity of the high-pitch copper film. So with increasing the peak current, the field thickness and the crystallinity of the film are increased, and the result in the decrease in the resistivity. And when the deposition time over 3 minutes, and with the film thickness around 100 nanometer, we can find the resistivity is significantly drop to around to about 5 micro-ohm centimeter. This is because the film will go to the continuous growth structure. In addition, we also can find the resistivity of the high-pitch film is very close to the theoretical value of the copper. And then after the film attenuation test, we can find all of the sample inhibit the highest rank of the 5B in the type test. So it demonstrates a strong film attenuation between the copper film and the PU substrate. Here we go to the EMI shielding performance. So in order to understand in order to better understand the effect of the peak current on the EMI performance. So here we summarize those data and use the average EMI value to investigate the effects. So we can see when the peak current we can see the average EMI value is increased with increasing the peak current, and then when the peak current over about 800 amps, the EMI value can reach over the 60 dB. In addition, here is the deposition time effects. So again, we also use the average EMI value to show here. So here we also can find the EMI value is increased with increasing the deposition time, and then for the deposition time of 20 minutes, the EMI value can reach around 65 dB. So this value is very close to the copper foil of the 70 dB. So it means the quality of the high-pitch copper film is comparable with the copper foil. So we also take the commercial product to compare with the EMI performance. So in this time the commercial product is the is prepared by the evaporation of the silver film with 150 nanometer and a quite thick conductive adhesive with 3 micrometer. And then in our case, a 200 nanometer high pitch copper film was used only. So we can see from the data, the EMI SE performance of the high pitch copper film significantly better than the commercial product. So this is because and this is because the benefit from the high density plasma in the high pitch process. So finally, we go to the feasibility and the durability test. So we can see when the high pitch copper film the high pitch copper film subjecting to the bending at the bending radius around 2 millimeter, and the resistivity will increase significantly. This is due to the formation of the micro crack in the high pitch copper film. And then after the dynamic bending test with the bending cycle over 10,000 cycle, we can see the resistance and the EMI SE value maintain a constant value for the high pitch copper film. However, the commercial product will be decayed. So we can see after the 10,000 bending cycles, the EMI SE value for the commercial products will decrease to about 45 dB. So finally, we go to the conclusion. So overall, to say, by taking the advantage of high density plasma, so the proposed high pitch copper film can be considered as a promising material for the threshold conformal EMI shielding application in the high frequency range. Okay, thanks for your attention.
Thank you, Pinyan. Yeah, so something soft and it really goes and achieve the functional need from EMI shielding purpose. So do we have any question for Pinyan? Yeah, okay. Here, okay.
A very nice talk of the professors here. I was just wondering, it's very good technology to deposit the copper for your copper film for EMI shielding. And you notice that you talked about the resistance will be much higher or lower, around 100 nanometer, right? Resistivity.
Resistivity will decrease.
Decrease, right?
Here.
Decrease, right? So along with the thickness, the resistivity will gradually decrease, right?
Yes.
Okay. So, but I didn't see when you go to the 400 nanometer, the decreasement is not enhanced dramatically. Is there any specific reason? That's the first question.
Okay.
And the second question is maybe the too future to talk about right now. Is that possible to make this process as like roll-to-roll copper film process in the future? I think that would be enough.
Okay, thank you very much for your question and your comments.
Okay, so I think we can see because during the silicon deposition process, the mechanism for the silicon growth will pass several stages, such as iron structure and the netting structure and the continuous fin growth structure, and so where the fin So when the fin sink is over 100 nanometer, I think the fin growth stage will go to the continuous fin structure. So the resistivity did not significantly change over the temperature time. That's the first question. And the second is the possibility for the low-to-low deposition. I think is yes. Yeah.
Yes, of course. There is no secret.
Yeah, secret, yeah.
Because we are a laboratory, and now it's already shifted to Dayong Beckham.
Yeah.
They have a commercial roll-to-roll system.
Yes.
So they have already demonstrated ability.
Yes.
That would be no problem.
Yes.
Yeah, but a bit of difficulty, of course, the control, which is what we are aiming at within this project, right? Okay, and I know what you're thinking. You're thinking of at a very low deposition time, what's at the same time atom by atom, layer by layer growth, rather than island growth. For high PIMs, it depends on what material you are doing. For copper, you will suffer less amount of island growth in the early stage, as opposed to silver, because silver is with very high cohesive force. So very in the early stage, you cannot escape away from island growth, even high PIMs. That's my experience. But for other compounds that you are interested, that definitely has layer by layer growth mode in the early stage. I don't know if you agree with me, Ralph. What material are we talking? For silver.
Yes.
Yes.
And so you first form more and more singular cluster, and you cannot shift to lower thicknesses. There are other materials, like you said, with copper or so, that works fine. With silver, it's exactly the opposite.
I see. Okay. Thank you for the supplement. So because of the time, we have 10 minutes behind the schedule. So thank our speaker again.
Thank you.
So one of the very important topic today in this morning is the message brought by Mr. Guo, who served as the project office manager in ITRI and also transfer a lot of service and information from DOIT. And today he's going to spend 5 minutes talk about the scheme in between Euro and Taiwan. Warm welcome.
Nice to meet you here. It's my honor to be invited by Dayong Vacuum Equipment and also by the Fengshan University. Then I have this chance to be here and introduce some kind of information to all of you. Before this, I would like to know, we know that doing research and development is investment. It's not like doing business. So at that moment, if there's someone or your government can give you a hand, that it's nice to have. So that's the reason why I am here today. I want to share just one information with you. It's about the funding scheme between Taiwan and EU. So you just remember this, that's enough. Today, I will focus on DOIT's program because each like MIRDC, we are the RTO and supported by DOIT. And we are helping the DOIT to promote the international cooperation between Taiwan and EU and also with Israel. This is the program supported by DOIT. It's an A+ program. Under this program, there's a special program called named Special Program, and there's an International Innovation and R&D Collaboration Program. So here's the QR code. If you have the interest, you can go into the website and check. Maybe you can find something, information valuable to your company or your organization. But before this, I would like to emphasize that this program is focused on innovation and focus on R&D and also focus on international cooperation. So that's the three key elements you can keep in mind if you want to apply this program. At this moment, we help DOIT to build the platform between Taiwan and EU countries like Spain, the UK, and Germany and Czech Republic. Since 2016, but for EU program, it started very early since 2008. So you can see that from 2008 until now, they have 58 projects approved, and the successful rate is around 24.6%. For the budget, if you apply this program, you can get up to 50% subsidy from DOIT. Here is the overview of this program. I don't want to explain too detailed, but you can see that the applicants from this program is focused on the industry. But for the Germany, if you want to find a partner to apply this program, you may need to pay attention. You need to find a SME from the Germany side. That's something different between German and the other country. For the EU, there's a program named Horizon Europe. And also there's another kind of program like Eureka Global Star or Eureka Cluster, something like this. So if you have the interest, you can go into the website and you can find there's some consultant telephone number. You can ask your question. Okay, for this moment, it's Horizon Europe. And for Eureka, there are 3 types of programs, but we focus on global stars. And that's a bilateral program, as mentioned before. Here, I want to introduce one more information about the Eureka Global Star. This call is not to happen every year. It depends on the need. For this year, we have a Taiwan call in cooperation with France, Poland, and Slovakia. So if your company has a topic with the partner from these 3 countries, you may think about this, but the duration is until June 20th. So it's a little bit not very long. That's a procedure. I don't want to tell you too much, but for the proposal stage and submission stage, we can help you on this to prepare a well application document. And after that, when you submit your proposal, then they will have a committee. They will evaluate your program. And also from the other side, like in Germany, they also have an expert to evaluate their program, their proposal. Okay, so this is in Chinese version. So I would like to stop here. The project formed by Dayong and Feng Jia and Process and Fraunhofer is one of the successful case for all the projects. So we are looking forward to having more projects like this project and in the future. So that's my information to share with you. Thank you.
Thank you, Mr. Guo, for delivering such an important information for us, and just grab this opportunity because this will let you open your eyes in cooperation with your overseas partner, if I may say yes. Right, so they agree. So thank you very much. And because of time, let's thank our speaker again. A bit of announcement from our side is the lunchtime 102 and 104. And for our speakers, please go to the third floor because there will be you're hard working because a bit of a space for a bit of relaxation. And please come back at 1 and 10, right? 1 and 10. Yeah, please enjoy your lunch. Thank you very much.
Move to room first floor 102 or room 104.
Afternoon session. And our first speaker from Plazas, Germany, Dr. Thomas Suter. I saw him many times in the international events, international conference, and his product selling all over the world. And I visited his company in Germany, close to Usper. It's mailing, right? And it's a small company, but it's a beautiful company with quite a lot of innovation going on in his company, and perhaps the most professional optical emission system in this world, and providing a variety of products. And as you can see on the booths, exhibition booths today, and when talking about plasma is like a black bus, and then by using this kind of optical emission system, open the eyes to see the black box of the plasma. So it's very important to see how he can do control. So the time is yours. Thank you, and let's give him a warm welcome.
Thank you, John. Thank everybody for being here. And I'm very happy to be back in Taiwan. I haven't been here many times before. And after these 3 years, I'm very happy to see you all in person again. We also enjoyed this in Europe, in Germany, to have meetings again. And I feel really honored to being here part of this forum and showing and presenting something which we do basically in our company at Plazos. Today I will focus on the high pumps application. We have a broader range, but since this is mainly about high pumps, I will show you some of the latest developments which we do for high pumps control. But let me give a few words to our company. Our company, and this is what also said before in the presentation, we are a very, very typical small business unit of Germany. Germany lives from a lot of business units which have a rather small core team, highly sophisticated, like we do have, like John said, but highly sophisticated persons. And that is what the German industry drives. They are very innovative, these small company units. But they don't, of course, they do not do everything on their own, but they rather have technology partners. And that's what we do have also, like the Fraunhofer here, but we do have other companies who develop the hardware with us, who do the development with us, who do application processing like Robeco. Both are located in Germany. Then we have the Fraunhofer, and now I'm very happy that we have now also a partner here in Taiwan with Dayong. And we are very happy about this project to have this, and I think it's very successful as well with FCU to give the scientific input for this. What we have done before a long time with the Fraunhofer FC, with Ralf Bandorf, which is not only a colleague to me, but even a friend, I can say. Okay, that's a little bit here. And We have a worldwide network. As John said, our systems are around the world. In the US, we have a strong distribution partner. Of course, we have a lot of distributors here in Europe. But we also do have Asia. Here we have applied OptiVac technology. Robert Jen is in the audience. You know, he's our main contact here, and he stretches out his arms also to other countries like Japan, Korea, and China, for example. Okay, our product range, and this is only to show you what we have here, consists of a lot of kind of monitor systems for different applications. Today, I would speak basically about the SA, which stands for standalone high pimp system. We do this also have without high pimps. We have an MC more for an R&D. This you have seen, and which is applied by Professor Lee from the talk here in the morning. We have also a special system here, and we have a new product, a layer control system. This will be introduced later by my colleague Jan-Peter Urbach here, so I will not talk about this. He will present that. Now, talking about plasma, looking into plasma, you need optics, and here we have also a variety of in-vacuum optics with a special design, which has a protection device on top, so it will not be coded during the process, and you have a longer lifetime of these products, and you have secure measurements. And of course, we do develop our own software for these different products. So where are we around? Basically everywhere where there's a plasma. We are not sticking to high pimps, to sputtering, but there might be PCVD, there might be etching, there might be ashing, there may be different excitation mechanisms. We, as a control mechanism or a monitoring, we do not care. We just look at the light of the plasma. That's what we do. That's what you do with your eyes. If you go through your viewport, look at the plasma and see, oh, now it's yellow, now it's green, now it's violet, and that we make use of. And this is here depicted here, right? So we have a collimator here. It's an in-vacuum collimator looking onto the plasma, putting the fiber into our system, and what you always get is now here a spectrum. You have seen this before, but I want to emphasize we have a 200 to 1100 nanometer range. That means you need the UV range. It's very important. Otherwise, you will not catch up the light from most of the metals which you are interested in. And now you can use this equipment for all plasmas, no matter what, because the rest is done all by the software. The software by software now, you pick the lines you are interested in. That are the species. This is Mother Nature. The young lines belong to species like argon, like silicon, if you go for a silicon target, like nitrogen, oxygen, and so on. And then you can track these intensities, which are related to the density in the particle over time. And this is now actually what we make use of. And if there is a deviation, or if you open the gas valve, you see that immediately in our monitoring tracks here. And of course, then you can give a feedback control. So that is our main technology, what we apply to different kind of plasmas. This you can do in a single channel. Single channel means that you have one position where you look at, and that is here for the collimator in the middle of a cathode. If you go now for industry coders, they have larger cathode, and there you might balance the upper and lower, or left or right, or we look at our part by different gas piping, especially in reactive gas processes, reactive gas sputtering. So for this, you need multiple sensors, here three sensors, for example, and each sensor is now controlling the sector of these different cathodes. So we have single channel systems and we have multiple channel system, which means each channel gives a complete spectrum, but from different positions. So for this, and now I will go into the system where we have done also the work together with Da Yong here in our Taiwanese-German joint project. This is a standalone system. This can have up to 8 different spectrometer channels, spectral range, appropriate spectral resolution, and time resolution down to 1 millisecond. You do have another feature. You can put in other sensors. I will come back to this later. And then, of course, you have control features. So you can give back the information you have analyzed and give it back to the controller, to the PLC, or to your mass flow controller to control the reactive gas flow. Since this is a standalone system, the processor unit is integrated, and we do have industrial interfaces. That's very important, and that is more or less, I think, still unique what we have here. We have field buses, several field buses already available, Profibus, Profinet, Ethernet IP, but we have also our own software interface with the LAN APE, where you can put it into your own software and address our system directly. Okay, here's now a typical, I start with a typical sputtering application, even though many of you or all of you know what's going on here, but here I have put a little bit of challenge. So we have a moving substrate. So if you are in a lab, usually you have a static substrate. That's rather easy, but if you have a moving substrate, and often you do have a moving substrate, you need to control also a reactive process. So what is the setup here? You have a dual cathode, for example. You have an aluminum process, so an aluminum target with argon, and you want to produce an aluminum oxide layer, transparent aluminum oxide layer with approximately this refractive index. At this moment, I do not care about the refractive index. I just wanted to show you how the control works. Now, what you see here on the right-hand side is, again, our software. You see here the aluminum lines, and you see the argon lines, and here the oxygen lines. And now what we monitor is not the absolute signal. What we monitor is a ratio of our aluminum to argon, because this gives you a more stable information, because you kick out the electron density in the equation which we are using to do this. So what you see here is that you have back and forth. You see a little bit of a ripple in the control signal. This was actually really controlled by a 35% signal of the aluminum to argon ratio, but the ripple comes from moving back and forth. The important thing I want to show you is here that the control does not get out of control. So it always comes back. So, and with this kind of feedback, you can have a very stable control, and you can minimize, even if you go further with this, minimize the not usable edges, for example, of a glass, where you come back to the coating. Okay. Now, this was DC sputtering, DC sputtering or MF sputtering. Now we go to high pumps. Everybody knows what high pumps about. I don't have to talk about this. You put high power pulses. Now, what you didn't see maybe before is what's inside the high power pulses. And that you see here. So you have this is now a time resolution of 5 to 50 microseconds in high pumps pulse. So in the beginning, you have some argon lines, green and blue. And here at the very end, you have the iron and the metallic lines. And that actually we want to monitor in a high pump application. Now, can we do this? Can we do this with the Imicon system? We can do it right away. Because from a spectroscopic point of view, an ion is a new particle and has different spectral lines. So, and that's what you see here for some examples. You see for copper, titanium, chromium, and silver. And in a high pumps application, the neutral lines as well as the ion lines. So you do not need to change any hardware or whatever. It's right there. You just have to pick it by software. That's what we did in our joint project. And this is some nice data from the IoT, from Stefan Körner actually, where I wanted to show you if you go from just starting with a metallic high pumps application and a copper application, you want to see what is the ionization degree. How many copper ions do I actually have? Now, what is the setup? Here, you do actually have the, this is a copper spectrum. You have the copper neutral line, you have the copper ion line, and then you make a ratio. And the ratio is here. And now the same, if you increase the peak current, we have learned that before the presentation, if you increase the peak current, you will see this scale here. You will see also the signal of the copper plus to copper increase. So you get more and more ions. So this is already to monitor where I am with my ratio. And of course, you can also control it if you want to give a feedback, for example, to the generator, or if you can. Okay, so far so good. Now going one step further to the reactive high PIMs. There is a little bit more challenging because we have heard this also before, and you have seen this picture from Shimizu, that not only the peak current is influencing the ionization degree, or otherwise the ionization degree comes with the peak current, but the peak current changes also with the reactive gas flow. So you cannot really tell what now really influences the peak current, and you cannot tell from the peak current about the ionization degree and the reactive gas flow at the same time. So you need an independent control for both. And that actually we put now in our system. And this is now the Emicon SI high PIM system for an application. So what we did, if you have 3 channels again, you have bottom, top, center, bottom, for example, same as before. But now we also pick up the voltage and current curves from the generator or from probes of the cables. And this is completely new. And we have put this in the same system as an additional, as an add-on module. And here we have 2 inputs and a trigger signal. Of course, you need everything to be triggered, so you are safe that you get always the same information from the pulse and from the spectrum. And then you have analog inputs where you put the voltage curves and ion curves inside the Emicon system. How does it look like? Like technically talking, very simple. You put in the fiber as usual, then you have the voltage and the pulse voltage and the pulse current inputs here in this additional module, and then you have a trigger. So with this you can monitor, but again at the same time we have the outputs, and then you can control the mass flow control for the reactive gas flow, and on the other side also the pulse generator to control the peak current, or at the very end it's the ionization degree. And this I will show you in the next slide. First of all, how does it look like? Now, if you have no information collected also in one system, and that is one of the topics which I discussing with Ralph Bandorf a long years ago, why don't we put something in the same system, getting all the information at one point, and then giving it further to the PLC to do all this, I put it, digital stuff. So what we see here is we have the 3 spectrometers, and then in addition we have the pulse voltage and pulse current. Consider this like an oscilloscope in our system, in our Emicon system. The advantage is, and that's what an oscilloscope cannot do, is that you can make now here a monitor track, because this is a monitor track, like you have done here for the spectral lines, and monitor now the voltage or the peak current, or even the shape of the peak current, and make advantage of this and look where I am with my process. And then here in the beginning, you see as an example, the monitoring, the real-time monitoring of the different signals. If we go now for a real application, and this is now for an aluminum oxide application, was a different one than before DC. Now we have high PIMS application, and I want to show you how this works. What you see here in the picture is only the monitor track, the aluminum line, pulse voltage, pulse current, and also argon and oxygen line. This is a metallic mode. Now we switch on the reactive gas flow and go to the 40% aluminum set point. What you see is it goes down. Yes, that is what is controlled. At the same time, you see the pulse current goes up. But you don't know what's going on now with the ionization degree so far. Just to show you, if you go one step further, you drop to the 20% point, and the peak current goes up again, and you get more and more arcing. That's quite usual if you put more and more oxygen inside. Okay, and if you go back, you have the same situation as before. These ripples are here, oscillation are due to the rotation of the cathode. So this is quite usual in this situation. Now what we did now, we introduced the control of the peak current, and we kept the peak current stable. And that I wanted to show you in the next slide. So we did the same thing as before, but rather keeping the peak current stable. And of course, the pulse voltage drops. So we did something, you have less arcing here, but to show here that you have a constant peak current. What does it mean now for the ratios we want to control. And this is now my final slide to this kind of control. So what you see here on top is you have the aluminum-argon ratio I've shown you before for the DC and now for the high PIMS part. This is now the high PIMS application, and we go from the 60 and 40 to the 20% point. Everything is controlled, reactive gas control by the aluminum-argon monitor track signals. Okay, and here below you see the aluminum plus to aluminum ratio, so the ionization degree in the plasma. At this point in the beginning we did not control anything, and as we have seen from Shimizu, with increasing reactive gas, the peak current increases, but also the ion increases here, okay, to a specific point. And from here now on, we even controlled this ratio, so the ionization degree, and went back to 40%, 20%, 40%, 80%. What I want to show you that here is now a precise control of both properties you will need, in my opinion, in high PIMS application. Not only the reactive gas, so the stoichiometry, but also on the other side, the ion density, the ionization degree. And that is what we want to provide with this one. And for R&D, you have a great playground to see where I get my best morphology with the best stoichiometry for my application. Going for industry, you need to show that it works, let's say, forever. Production, you know. This is what we done with the Fraunhofer. Ralf Bandorf and his colleague did this, a 7-day run for this application. It was now a different application. We don't care what kind of material there is, you know. So we skip, we jump from one material to the other because we want to do the controlling. So here we did a titanium oxide application, and this was a 7-day run, and we wanted to show that this can run for 7 days stable. In the 2 days in the beginning, we had some problems, seeing some faults, seeing something happens, so we needed to take care of it. But at the very end, the last 5 days, everything was stable. It was running day and night, continuously controlled. And that is what you need actually in production line, whether it's a web coder for hours. Here's now days, maybe it's 4 hours. But if you think about glass coders, for example, they run for days and weeks even. Okay. Putting all this together, what I wanted to show you today is one thing that not only the spectroscopic sensor can be fed in one of these systems. At the same time, we have then generator sensors, like, for example, what I showed you for the high PIMS, the IV curves, you know, and make use of it all in one system. At the same time, and Stefan Körner talked about this before, you can put in also other probes which you have, like a lambda sensor, in our system by giving the voltage from the lambda sensor in our system and put it as a monitor track. So you have this information also in our system. We have the VI sensors, and you can also adapt our new layer control system from Jan Peter, which he will present later. And now, having all these data in one system, you can make now an advanced and smart control and control several things at the same time. Reactive gas flow and ion density, process stability. You can look for system health, battery producibility, impurity detection, or you can do even an endpoint detection. There are more. I just want to show you, if you put several things in one system, and that is what we are heading for at our company, you have a wide range to make your process really stable and producible. Okay, since I'm good in time, I will let you know what our next generation Imicon will do. At this moment, we are here at the left picture. So we have a high PIMS pulse, and we have in our system an integration times, which means an exposure times. How long can we look at the plasma to get information from the plasma? And the minimum integration time at this moment is 1 millisecond. That means for a high PIMS application, you do not resolve the pulse inside. So you have always 1, 2, or even more pulses. So you have a pulse average measurement. The idea now is, and I've shown you this picture before, what we need in the process is the ion density, the metal ion density. How do we know when the highest ion density will be in the pulse? And that we are doing now, right now, developing a system which has a reduced integration time of about 10 milliseconds, which is here the pink area. And now we move it over the pulse. And by moving this over the pulse, we can detect the peak of the metallic metallic lines. And then we can trigger the bias, for example. If we at that moment trigger the bias, we attract the ions to the substrate, and then we might have a better deposition rate. We might influence the morphology and so on. So this is what we are heading for, and we think this makes the high PIMS application even more worth and industrial-like as before. Actually, this system should have been on the market right now, but we were also suffering from the chip crisis. So unfortunately, we had to redesign, and we have to do 6 to 9 months work again, losing money, but that's the way it is. But now we are again back, and we are developing this. So this is now scheduled, the release of this system for fall, maybe summer, depends how it works. For the summary, I wanted to show you that you can have an advanced technique for metallic and reactive high PIMS control, controlling independently the ionization degree as well as the reactive mode as an example, and putting in even other sensors. So this secures you in industry production. Securing is always very important to do everything the same time and getting the same result. As a perspective here, I think you have new opportunities with this kind of system, with this kind of control, and of course towards digitalization, we have so many things already in one system, and give it then back to, or not back, but give it to the PLC or give it to your database and so on, as one system, which makes it also more easy to digitize all these data and bring this together. And with this, I want to thank you. And if there's questions, I'm happy to answer them. Thank you.
Thank you. Thank you, Thomas.
And I promise I'm under control with the time, right?
Very precise control.
Try my very best.
Yeah. Okay. That's
Sorry.
definitely. It's okay. So you mentioned about. Sorry, it seems like I'm the audience. Sorry, questions to audience, because I'm so curious about your technology. Do we have? Oh yes, Jeff.
Yeah, thank you. Yeah, Thomas, thanks for your excellent talk. I'm curious about one situation is, for example, we are working on the titanium oxynitride with the 2 different reactive gases. Do you know how to control probably for these 2 reactive gases?
You want only every time one more, but it's okay. No, actually from the spectroscopic point of view, to monitor these different species, no problem, as I've hopefully shown you before. So you have the titanium, you will see the nitrogen line, you see the oxygen line and so on. Now, the rather challenges is how to control this, because you cannot go only by the titanium line, because you don't know whether the poisoning comes from the oxygen or from nitrogen. So you need to have a mixture of, and that depends on your working point, maybe control the nitrogen by the nitrogen line itself, and go for the oxygen by the titanium line. Because, yeah, that's one of the points. And I have to mention, if you do this, you need to have really a good gas piping. It's very important. And you need a good pumping, let's say a good setup. That's important. But from general talk, you produce a huge amount of data. You need maybe for one day 2 terabytes. No problem for us to produce this kind of data. for R&D. You know, if you just go for production, then you can reduce everything by the monitor tracks. So it depends on the situation, you know. But also data storage is also no problem, you know. Then you get another 5 terabyte hard disk or SSD, whatever you like, you know. Yeah, but then I'm with Ralph. What you do with all this data? Here are so many students, right? They have to look at it, right? Yeah, and this is what we need actually for digitalization, having artificial intelligence, getting squeeze out the data like this Sir mentioned before, you know, getting really the point. And here we want to also give some contribution, you know, to make a kind of pre-analysis, you know, but then giving this data to further process in the digitalization mode. Mm-hmm.
Mm-hmm. Great. So that could also respond to you in the morning, your questions. Who needs so many data? I believe that our graduate student might need it because they might have a lot of set of parameters for evaluation, I think.
Yeah, I mean, if you're a student, you have to learn the basics.
For
that's
R&D
the point. That's you have to know what you're doing. You know, once you know what you are doing, you know, you don't need to know the exact details if you do it right. That's always a point. You know.
Yeah, right.
So young people have good innovation, high spirits, everything, but you need also some experience, to be honest.
Exactly, and at least you should know the arrow, the direction you're shooting.
Yeah.
Right. So, do we still have time? Okay. Another question? Yes, again, please.
Okay, yeah, thanks again. Yeah. All right, as we know, for the past years, using the time-resolved OES, we usually use a high-speed camera to catch all the information. And how about in your case? Do you have any secret about that? It seems like you already skipped the usage of the high-speed camera, right?
Professor Lee, thanks for addressing this point. I wanted to tell this here, you know. Usually you need this very high cost OAS, high-end system, which costs, I don't know, $100,000 and then you can do this. In the last years, the detector errors, which we are using in our spectrometers, became better and better, okay? So there are big companies like Hamamatsu and so on. Now they provide detector errors, which you can pay for, even in industrial case, you know, and they provide this kind of time resolution. It was just before not available. So also to them, you know, they made it available and now we just picked it, you know, and put it in our system, you know. I don't tell you which one it is, but it's not really a secret, yeah, but this more or less the IP here is to read out it, to get the data where you want to have it and to synchronize everything. That's not so easy. Yeah. And it's still kind of cost. It's a little bit, of course, we have inflation, you know, nothing gets cheaper. Sorry about that, you know, but it's still in the price range as before, you know, otherwise there's no, and it's continuously running. That's also the difference to these high-end OES systems. Okay?
Okay, and there's one, sorry, please, 1 minute. Okay.
Hi, we've been mentioned about the time resolution, but nowadays I've realized in some way the spatial resolution could be a problem as well, due to the possibility of the inhomogeneity of the processing chamber, which could bring significant differences of result. So have you ever think about or in the future, do you think about the spatial resolution coupled with time resolution?
Yeah, I've mentioned here, sorry, we skipped already to the next presentation.
Okay, sorry.
No, but I can answer this also by words, no problem. We have this, we call it HR system, which is a high resolution system, and this means now high resolution in a spectral sense, okay? So this has a higher resolution, spectral higher resolution, and that would be, to be honest, the next step. First, we go for our normal standard resolution, you know, and go for the high time resolution. And then we go the next step for the high spectral resolution. And so then we have both, you know. There's a special technology we have behind, but we are working on this, and this is possible. This is actually only a small step, But talking about high resolution, you are talking, I think, especially about specific application where you not really separate lines one from each other. Yeah, I think that's what you are talking about. And then you need a higher resolution. In what we have experienced in all these high PIMS applications and in most of the industrial applications, it's not necessary. If you go for etching, if you go for some PCVD application, you might need this. But this you have to check. Okay.
Right.
Does it answer? Yeah. Oh, okay. Sure.
Yeah, that's the point. Well, if I am not a responsible guy, I would say that's your problem because your plasma isn't so uniform. It's not his problem. It's, I'm joking, but you know what I mean.
Yeah, but on this also, we do help with this. We know this is maybe a couple of words to this, We are really want to give a strong support to our customers because we know not everybody knows this spectroscopic emission monitoring technique. Once you are in, it's rather easy from my point of view. Okay, I've done this now for 35 years, but if once you have stepped in and you have caught the idea what's going on, it's rather easy. Right. But the first steps are not so easy, and here we give always strong support also to our customers.
Yeah, sure. That's why people respect this company. Yeah, please.
Maybe also one comment, because if I got your question right, it's also about the distribution and the inhomogeneity of the plasma. It must not be that you control it with the optical means. You can modulate your chamber. You will have dynamic effects also by the substrate motion and so that don't depend so much on the reactive process itself, rather than on your chamber conditions and the process. So you can use other tools like what I showed, the plasma modeling code, where you describe what is happening, where is some poisoning preferred, and those things. And if you tailor those, and I'm not sure whether Professor Tang will mention that, if you have a shutter that is adapting and things like that with your configuration, and then you go for the process control with the optical means, because you don't need that amount of fiber or that real image of your system itself for the control. But you need the knowledge before, and that was the discussion we had, to get the feeling, to get the experience, and to know which are the factors you have to address. But this one, you don't need to control with the optical means, with the feedback system, but you have to tailor your whole system and the design of your machine and the other boundary conditions for the process.
Sorry for not understanding your question. We can talk later. Sorry, I didn't yet catch the point. Sorry.
Okay, so thank you. Thank you for our speaker again. And then the next keynote speaker is Professor Yoshinobu Kawai, who stay in this field for more than, I think, 40 years. And he's also our chair professor in Department of Material Science. And he heavily involved in plasma diagnosis and the high frequency plasma, semiconductor etching, etc. And he is the pioneer of those plasma process, particularly for solar cell and also for plasma etching, a lot mention of high PIMS. So please welcome Professor Kai.
Thank you, Professor He, to introduce me. Okay. I have been working at Punjab University for 11 years. 11 years already. And so maybe 5 or 6 years ago, I joined to Professor Hu's group and then started high HIMPS. And Professor Hu had, still have, has two good system to measure the plasma parameters, ion ion energy analyzer and Langmuir probe systems that I will explain here. Both are coming from the impedance in Ireland. And unfortunately, to is good and very expensive machine did not work. Then so I asked the student and to start the measurement using the homemade, we call so-called homemade Langmuir probe. Just very interesting, simple. And then, but high Higgs is very high density. I never studied for such a high density plasma with the Langmuir probe. Then so we need a very low resistance, low resistivity, and high power. Then so because the high density high, then so current very high, or for example 1 ampere. Then so 1 ampere and 1 ohm, giving the 1 watt. Yeah, very high. Then so I bring the distance from Japan, and no problem with the custom. And then so then so now the former talk showed you the very interesting and very wonderful method to control, to monitor the behavior of high Higgs. But to me, it's high Higgs plasma discharge has not been understood. There are still many lot of problem subject. So please, young student or young researcher and industry, join to the Honsha University as a PhD course, and then to study the plasma behavior of high Higgs. Because I'm old then, so I cannot go on the. So then, so I strongly want to student to come to Professor Rabo and to study to high Higgs discharge behavior. So, next one. Done. Yeah. Oh? Hmm? 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 Oh, this one? Back. Okay. So now I like to be talk about the introduction. As I already told you, there are many interesting subjects in high Higgs that are not understood. Yeah. And then so here is here we have studied. Mistake. Oh, yeah. I am using the PPT file that is used for giving a class at the Honshu University. Those are Lagrange probe. Just you can introduce metallic wire, okay, very thin, and that was proposed by Lagrange. And he just use okay, you hear plasma, and then so introduce wire, metal wire, and apply the voltage, and you can get the current. You can the probe. We call the probe. Name the wire. That's called the probe. Okay, just a simple wire. Then apply the voltage called the probe voltage (VP), and the current called the probe current. Okay. And then so that's it's something like the IV curve of sheath. When you introduce the metal, then so sheath form on the wire, and maybe Langmuir's it's proposed idea that's coming from the IV curve electron tube. Then so that is a IV curve, and obtained IV curve shown in the solid line, and actually then so we assumed electrons, and Langmuir assumed the ion also Maxwellian distribution, but that was wrong. Yeah? But anyway, then so now we assume the electron and Maxwellian distribution. Then so this current plasma consists of electrons and the ion. Then so when you introduce the flow, then you can have the two current. That's called the electron current and electron current. Then so that okay, and then so we assume the electron have a Maxwellian. Then so like this Maxwellian distribution, that electron current behave as a Maxwellian distribution. Okay. And also here you see that you have the saturation current. Yeah, okay. That is the electron current that's called the electron saturation current. Ion this region also ion saturation current. Both saturation current provide you the information about electron density because both current is proportional to density, electron density and ion density. And then also this slope, as I already told you, it's electrons are Maxwellian. Then so this current is exponentially going down. Then so you can estimate the electron temperature from this slope. And also plasma, it's a plasma potential, Vs. Okay? Yeah, it's this point. Okay? And also later I show you the actual measurement of a floating potential, but very easy. Just you can bring the oscilloscope, then to measure the floating potential here, because here the current equals 0, okay? No current. Then this called the point Vf is called the floating potential. Then so yeah. That is a example. A Russian guy, Oskirovko. It's IV curve bipolar, I think. That published in 2019. Okay. this one. Then unipolar and bipolar, you see. Then so here's a point called plasma potential shifted to higher. Then that means the plasma potential is positively high. And also here, floating potential also shifted to the higher. This is to me, there's no meaning. Yeah. And unfortunately, their result is time averaged. Time averaged. Maybe they don't have the good oscilloscope, US oscilloscope, Tektronix, maybe. Yeah. And so we try to measure the time resolved measurement. Experimental, and this time by bipolar, we can change the delay time. Here's we choose no delay time, but if COVID, then so the data we took it's just before the COVID-19. Maybe I remember we measured 3 times IV count with the student here, home student, not out. He's working at industry, and maybe in November, and the result was not good. December, very good, and on January 2020, and we repeated the experiment, and we are lucky to get many data. Okay, then so after COVID started, I could not come to Taiwan 3 years. Then so today's I cannot conclude our result, but I can give some discussion about my idea. So now this is the bipolar chamber, and we introduce Langmuir probe. That is 10 centimeter away from the target. And bipolar high power supply. But I was asked by someone, but I did not remember anything. Huh? It's a Taiwanese, yeah? Bipolar high power supply. Taiwanese, you know. Not unipolar, we use 15 line. I remember, yeah. The prototype is, until now, we measure the voltage and also current. Okay? And we will apply the DC voltage to Langmuir probe and measure the current. And we use oscilloscope, digital oscilloscope, to measure the current. That is a typical discharge current, discharge voltage for different pulse voltage, plus as a bipolar, as a positive voltage, different. And see that it is voltage, the negatively voltage applied, and then so some and also I forget to tell you, it's we use constant current mode, Okay. Then so to keep the constant current, then so voltage is changing. Then anyway, then so unipolar and bipolar, then you see that the polarity of current different. Okay, yes. Okay. This is voltage. Sorry, I missed this. This is and plus voltage up to 100, up to 100. But it's also very strange to me. That this is 400, okay, and but the 100, but the later I'll show you the plasma density almost the same. And this is also I do not understand it. Anyway, okay, and that is the current. Okay, then so you see that we use a constant current mode, and yeah, it's not exactly constant, but it's time a little bit fluctuating, of course. And that's roughly constant current mode. Okay, and then bipolar power supply operated. Then you see then so current. Also, you have the current. Yeah. And then so this is the negative current, mean the discharge current, the opposite side. Yeah? So the target now, in case of the bipolar, target should act as the anode. And then so Langmuir probe theory tell Vs is the plasma potential, and Vf is the floating potential. That difference is proportional to the electron temperature. That is the mass. Then so unfortunately we cannot have the mass spectrometer. Then so we now assume the argon and copper ions. Yes. And then so sometimes this is difference is called C's potential in etching people. And then so we measure the floating potential. Okay. And unfortunately, we cannot measure the plasma potentials in case of bipolar. I remember we want to get the electron current, and then so we increase DC voltage to apply the to the Langmuir probe, and suddenly we had a big serious problem. It's a Langmuir probe, the band, yeah? Because too much current, huge current. Then maybe it's commercial ones. With commercial ones, it may maybe to be able to measure the electron current. Then so example, it's Professor Anders use emissive probe. But the emissive probe also has some ion bombards the probe. You know? Then so he, I guess he protect the Langmuir probe, yeah, to avoid the ion bombardment. Maybe. Then I'm not sure that is you have some plate, yeah, to avoid ion bombardment. Then so near the emission probe, parameter may change. But I mean that then so then I met when I met the president of impedance, and he replied to me that it's possible to get the electron current. But unfortunately, we had COVID and impedance president Hopkins retired. And then so right now, I don't know what okay. Emission probe. Yeah. That is so floating potential measurement. Okay. That is a discharge voltage, as I already showed you. Okay. And here we apply the bipolar voltage. Then so floating potential, it's that is so it's you can say the unipolar. Okay. Then so minus some volt, okay, and apply the plus voltage quickly going up. Yeah. Then in this case maybe the 50 voltage or something like that. Okay. Anyway, then so if increasing the bipolar power, then so it's floating potential is also get scale over. Yeah, it's very high. And then so I now show you the floating potential behavior for different voltage power supply. Okay, you see the then so at 12.5 very small. Then so floating potential is not so different from unipolar. But increase 50, then so as I already showed this, okay. And 75, okay. And 100, and but it's you see it's during the unipolar phase, almost the same. Then plasma it's a parameter almost the same. Then so okay. This means it's okay, as a yeah, you see. Then so floating potential is going up. Then this means then so plasma potential also is going up. Yeah. Yeah. Okay. That is the sense on ions current. Then that is the minus 40 volts. And then so ion saturation current does not change with bipolar pulse. Same. Yeah. That then so plasma density does not change. Still, then so high density plasma is still kept during the bipolar. That's very, very interesting to me. And also, here you see the this is some unipolar. Then so it's by second pulse, and then you have the ion saturation current peak. You have some peak. Yeah, we call this is the second peak. We call it second peak. And second peak in unipolar was very popular. And many people, and also review papers tell about the second peak. And then so many ideas were proposed. But finally, Professor Gudmundson's review papers tells it is some neutral particles are reflected from the chamber. And then you have the high neutral density, then so plasma density increases. That is the idea. And last week, I joined the international conference in Japan and met Professor Gudmundsson, and he asked me, or second peak already understood, but then so I discussed with him, yeah, and then so yeah, he memorized my idea. Okay. Then so that is electron saturation current. You see, you cannot measure, of course. We need to high voltage to the probe to get the electron saturation current. Then we try, but as I already told you, the probe damaged. It's burned quickly. Then not possible. Yeah. Mm-hmm. Then so got this unipolar case. Unipolar case, you see that the ion saturation current, similar behavior. So ion saturation current does not change with bipolar voltage. That is the electron saturation current. We cannot measure. Okay. Hmm? What? What? Huh? Already finished? Finished? Hmm? What? Hmm? What the? Yeah, next one, next, yeah. Battery, oh, that, no. That is it's the electron density behavior in time. You know, time resolved. Then here the density it's we call the second peak. Yeah? We have the second peak after turn off the power. Then so we have the second peak. Yeah? We are interested in this second peak. Density is very high density. And that is the electron temperature behavior. You see that the turn on, then power switch off, then so quickly electron temperature quickly going down, and about 5.2 or 0.6 eV after pulse. Then so with this low electron temperature, you cannot make ionization. Right? Then so we measure the lung. I will carve on the carefully analyzed. Then so we found out that this this is long plot. Then so this slope shows the electron temperature, and you see here after this is after T-on. I mean, then so, this is as I already told you, the electron temperature is very low, lower than 1 eV, and also we have the hot track high energy tail, high energy tail. Then so Professor Anders' review paper tells electron accelerated, secondary electron is accelerated by bipolar, unipolar voltage. Okay? Then so maybe 100 eV or something like that, very high electron temperature per electron exists, just they exist. But after T-on, he does not mention about that. But here we found out after T-on, still we have the high energetic electron. Okay? Then so that something like a conclusion that here, then so bipolar, that is the plasma potential distribution here. Then so if you apply the bipolar second pulse, then so plasma potential expected like this, okay? And that's that potential voltage depend on the your power, okay? Then so bipolar means just you can control the plasma potential. Plasma potential. Usually you apply the bias voltage, okay, to the substrate. Okay? Then so, but then yeah, I'm, it's review paper says that did not observe increasing the deposition rate, but the quality is better. Yeah. Maybe then so this structure will give you a better film. So and that is yeah. Then so it's almost the same. Yeah, and that you bipolar unit high Higgs. Then usually is plasma potential 10 volt low, but now with bipolar plus voltage, then it's plasma potential going up to 100 volts, something like that. Right? Then so you can control the plasma potential with bipolar power. The power. Okay. Okay. Then so I cannot conclude our result. Just on the way to the conclusion. Then so now, so I will stop my talk. Yeah. Thank you for attention. Anyway, then so there are many interesting physics. Yeah. But industry people don't care about the physics.
Right. Yeah.
Yeah. But yeah. Then so I hope that all the students join to the PhD course of Hanwha University. Yeah. And then so you can make publication, no problem. Yeah, with the PhD course.
Okay.
Yeah. That is my conclusion. Thank you.
Thank you. I think what you are finding is all in good agreement with our common sense on bipolar high beams. And yeah, maybe our industry friends will then get to catch what we can actually control of the bipolar high beam. The point is that the bipolar high beam increase the plasma potential, which would very often consider as the technique by using plasma booster in conventional sputter system, sputter deposition system. Semicon, for example, use plasma booster before the age of high beams. So it's all in good agreement with industrial development. Okay, do we have any question from our audience side?
And I'm worried about the X-rays emission. There are high energy electrons there. Then so usually is a high energy, but argon is maybe okay. Helium or hydrogen, it's easy to emit X-ray because the electron energy is very high.
But you say electron temperature is low.
High. But yeah, Professor Anders never mentioned about that. Yeah.
Okay. Well, with a simple homemade Lamia probe, it could be like 50,000 ND dollars. Yeah, ND dollars, 50,000 ND dollars. I think the boss of impedance will not be happy.
Actually, homemade is better. And and I wrote to the Professor Anders. He also likes also homemade. He told me. But currently, I don't know what kind of probe he's using. He usually uses now emission probe to measure the plasma potential, only plasma potential. Yeah.
Yeah, okay. Do we have any question or comments? If not the case, let's thank our speaker again.
Thank you.
Thank you. And now it's a coffee break hour, so the time, please. We have 3 more presentation after the coffee break.
Yeah.
So Sasa, would you give an announce?
Okay, let's take a break until 10 to 3 in the afternoon. The coffee break is sponsored by Places and UVAC. Please enjoy. The next section will begin at 10 to 3 in the afternoon. Please come back in time. Thank you for your cooperation.
就先跟大家分享一下，外面有一个立牌，就在楼梯外面的那个楼梯走下去旁边啊。这个立牌的话，我们也花了一点钱看起来 beautiful，it's beautiful, right? So please photo with this stand and bring your memory some other time. Okay. After this forum, suggested by Stefan. Yeah. I think it's our time to move to the last session, 3 invited talk. And the first talk is presented by Dr. Jan Peter, precisely Jan Peter Urban, and he is also coming from process company, and he will demonstrate not only Amicon of the process, not only can monitor plasma, but also can help you to do layer structure as a consequence application towards color decoration purpose and reflective purpose for optical control and the design. So let's give him a warm welcome.
Okay, thank you very much for this kind introduction.
and also for the opportunity to present one of the latest or more recent developments that we did at, or still doing at Plasus. And this is, as you already mentioned, it's about layer thickness and layer and color control during or in situ, so during the process. So to give you a small motivation about why we are doing this, you heard a lot about our sort of main technology of the Plasus company, and that is that we are monitoring the emission of the plasma and we track it over the time so that you can see the plasma composition and how it changes within your process. And this is, we have been doing this for 25 years, or over 25 years right now. And so we thought that it is time also to do something, some extension. And while the plasma is obviously, oops, sorry, ooh, this was too fast. No, this is wrong direction. Okay, so while the plasma is obviously a necessary tool to create your film in the process, it does not give you a direct measurement of the layer properties. And this is why we're heading to a more direct measurement technique. And the more direct measurement technique is reflectometry. So what you're doing is you're shedding light onto your substrate and then you collect the reflected light to measure the reflectivity curve as a function of the wavelengths. And from this, for example, and I will talk to that a little bit more detail, you can deduce the layer thickness of the growing layer, and you can do this in situ. So you can, while the film is growing, you can see what the current thickness is right now. So this is sort of the principal setup. As I already mentioned, you have a light source, then you have an illuminating collimator, which sends light towards your substrate. Then you catch the reflected light by a second collimator. You feed it into the Emicon LC system. The LC there stands for layer control. And then the Emicon LC system will determine the reflectivity as a function of the wavelengths. There are also, no, too fast. There are also the possibility to join these two collimators into one, and this gives you the opportunity to really measure in normal incidence rather than at an inclined angle. All right, so this is some examples of setups that we have already realized in various applications. So for example, this is an example of this normal incidence measurement. You have the optic collimator here. You send the light through a viewport onto the sample, which would be inside the vacuum chamber, and the reflected light goes back into the collimator and is fed into the spectrometer. This is an example of this two collimator setup where you measure at an inclined angle. So this is the illuminating collimator and this is the receiving collimator. We also have a special optics for deposition processes with high deposition rate. And there we use a dedicated sample, a witness sample, which is mounted by a special fixture onto the optics so that we avoid the contamination of the coating to the optics. So the witness sample acts as a deposition protection device, basically. This one we added to the reflection illumination or the reflection collimator, also a collimator which detects the transmitted light, so we can measure both the transmission and the reflectivity at the same time during the process. And this is an example of the in situ optics, where we really have placed the optics inside a process chamber. In this case, this is an inline coating system for photovoltaic modules or wafers. All right. So what can you learn or determine from the reflectivity of a sample of a film? This is explained on this slide. So one obvious measure is the color of the surface. And to measure color, you just calculate, or you just You just multiply your reflectivity spectrum here by 3 different weighting functions, one for the blue, one for the green, and one for the red. And then you integrate over the visible wavelength range and you get 3 values, which are the color values, so-called. And from these color values, you can determine
sort of the color specification of various color systems or color spaces. The most famous one, I guess, is the CIE lab system, where you have one value for the brightness of the substrate of the surface, and then you have two values, the A and the B values, for the different colors. This is an example of lab measurements that we did on on different samples, which were coated with different thicknesses of the same film, basically. And here you see, in this table, you see the values, the LAB values that we measured with our system. This is a photo of the sample, of the real sample, and this is sort of the re-rendered color from these three values in some software. And you can see that the colors pretty well match the visual impression from the photo. And the differences is mostly due to the rendering of the different devices rather than from the error itself. All right. And so far this were lab measurements, but we do this also in situ during the process. And so you can see that while the film is growing, we can see how the color values will change during the process. And then when you want to have a specific set of color values, you can stop your process at that when you have reached those three values, and then you can tell your process control system to stop the coating process. All right. The next sort of obvious measurement or parameter is the layer thickness. If you have a transparent or semi-transparent layer, then you can actually determine the thickness because you have this interference effect between the surface and the bottom of the layer, and the two waves which will be reflected from the two interfaces will interfere with each other. And depending on the wavelengths, you get destructive or constructive interference, and that gives you a minimum or a maximum in the reflectivity and all values in between. And since this is a fairly, I wouldn't call it easy, but a deterministic mathematical model or principle, you can actually do a very well-defined mathematical fit onto the data, and from this data, from this fit, you can determine the thickness of your film. I should say, though, that you need a very good knowledge about your refractive index so that this fit will actually match the measured data. All right, and this is for the same set of samples, the thickness values that we determined, and they match pretty well the expectations that we were expecting from the process duration. All right, can we make this one the video? Right, so this is a video from an actual process data, and you can see now that how with the growing coating, how the reflectivity actually changes, and you barely see that there is a fit beneath the data basically, and this fit gives you here the thickness value of the growing film, and we set some endpoint value where we want to stop the process because we thought that this is the right thickness that we want to reach. And so the system will actually, once it reaches this thickness value in a moment, it will issue a trigger signal basically for your system control to stop the process. So here we go. So it will issue an endpoint reached signal, and then you can stop the process. All right, so these are sort of obvious, or I would say fairly common applications for reflectivity measurements, though it's not so common to do it really in situ in the process. But there's also some additional things that you can learn from such reflectivity measurements, and this is what I want to present in the rest of my talk. So we were using this technology on nanocrystalline diamond films and also on amorphous carbon layers. So this is sort of the setup again for the nanocrystalline diamond films. We had it's a PECVD process actually. We measured from the outside. This is the setup that I already showed. And at the same time, we measured also the plasma emission with our normal plasma emission control system. These are the process details, but they are not so much interesting for what I want to talk about, so I will skip them. And this is some laboratory measurements again on samples that we received before we went to the actual process. And we found out that we can actually measure these films fairly well. So the values that we determined from the measurement do match what they were expecting from the process. But then, whoops, there was one problem actually, and this is that those films are fairly rough. So these are SEM measurements from two samples, one with a thickness of 500 nanometers, the other one with 1000 nanometers. And you can see in the high resolution image that there are sort of crystallites with facets, and this will lead to a fairly high surface roughness. You can also see this here. So this is the bare wafer. It's smooth, so there is no scattered light, whereas this is the coated sample, and you can see this halo from the illumination, which spreads in all the directions. So this is the scattered light. And this scattered light actually will lead to an error in the mathematical fit that I just mentioned before. Because what you see here, the red curves, this is the fit that you would expect for this kind of wiggles in your reflectometry measurements. And you can see that the amplitude of these wiggles go up or are higher than what you're actually measuring. So the blue curve is the measured signal. And you see that the wiggles here are damped to the lower wavelengths when you have roughness. And we were able to cope with this problem by extending the fitting model by two more parameters, which includes actually the RMS roughness of the film. And so you can see that not only you get the thickness value and a very good fit, because the green curve is actually the fit and it matches the measured values very well, but also you get a value for the surface roughness. So not only you get the thickness of the film, but you also get a measurement of the surface roughness. All right? And then the other thing that we learned from those nanocrystalline diamond films is that they are actually, you can have some information about the growth mechanism or the growth model. And what people do when they're growing these nanocrystalline diamond films is, because the diamond will not grow on any surface, but it will preferentially grow already on an existing diamond surface. So before the coating, those substrates will be seeded by nanocrystalline nanocrystals with a diameter less than 10 nanometer. And then once you start the coating process, the diamond will grow on the crystals rather than on the surface. And it will grow until those seeds touches to each other, and eventually they will form a closed film, and then you will have a film growing. Now, if you remember that I was talking with this reflectometry model, that it's an interference effect. But at that stage here, you will have no interference because there are no closed films. So the reflectivity here is, the mechanism for the reflectivity is different, because the reflectivity here is governed by scattering rather than by an interference effect. So we managed also, or we included in our fitting model a parameter which actually describes the specular reflection. 5 minutes? Which actually reflects the amount of specular reflection. And you can see that in the beginning of the process, the specular reflection goes down, and then something is happening here. And this is reflected also in a very pronounced increase in the fit deviation. So this tells you that the fit quality deteriorates with the time. And then after this steep rise, the fit quality again gets better because the deviation goes down. And you're actually now in the regime where you have a closed film, and the interference model actually matches what you're seeing in the data. So what this tells you is that at this point here, this is the point where the film actually will start to close. So this is isolated seeds. Then you have a phase when the film starts to close, and then you have later on you have a closed film which actually matches the interference effect. And we did another experiment to really to check whether this assumption or this hypothesis is right, by just adjusting the seeding concentration on the substrate. So this is a lower seeding concentration, this is a higher seeding concentration. And you can see that with a lower seeding concentration, the film closing is actually shifted in time to a later point, which means that you need more time so that the film actually gets closed. All right, so the second thing that I want to talk about is an amorphous carbon layer. This is the experimental detail, but in interest of time, I will skip over those. And this shows the result from the reflectivity measurement that we got when we used a refractive index which we determined from an ex situ measurement in ellipsometry. This is what you normally do with those films. And you can see that the fit quality is not very good. I mean, if you compare this to the measurement that I showed you before, you didn't see these large deviations. In addition, you also can see that there are some kind of spurious deviations from a linear thickness growth at the beginning of the process. So the question is, what are these deviations and why is the fit quality so bad? Well, not as good as we would expect it. And what we did, we looked into more detail that maybe this is the process which gone astray for some reasons during the process duration. And therefore, so you can see here, this is again this spurious growth rate deviation. So this is the growth rate. And you can see that there is a dip in the growth rate, which is accompanied by a high increase in the fit deviation. So which tells you that there is something wrong. However, we can look at the process by this plasma monitoring system, and we can see there is no sign of any process deviation during this period of time. So something else is wrong. And we thought that probably the refractive index from the ex situ measurement is probably not the correct one. And we found a method to actually determine the refractive index from our reflectivity measurements itself, so we don't need any ellipsometry, but we can use a set of reflectivity data to determine the refractive index. And with this new or in situ reflective index, like marked here, we can see that actually the growth rate is now more or less flat, and also the fit deviation is much better than with the ex situ refractive index. And this is in line with the process stability that we checked with the plasma emission system. All right, this is my last slide basically, because now, since we know that we have a very good fit deviation because our refractive index is good, we can trust that any fit deviation is actually caused by something in the process, and this is shown here. So here we deliberately, so by purpose, we changed something in the plasma. It was just an increase in power, and we see that this power increase will increase preferentially the hydrogen content in the hydrogen emission in our plasma, so the hydrogen content. And you can see now, okay, the growth rate also goes up, which is not so much surprising because we increase the power. But what you also can see that the fit deviation after some time gets worse. And this is an indication that actually the refractive index has changed and therefore something in the process has changed. Okay, so this is basically the final slide of my talk. So I want to summarize. I have shown you hopefully that with the in situ reflectometry, we can reveal useful properties of thin films like color values, thickness, also roughness, and also we have a mean to determine the refractive index from those in situ measurements. So we can monitor the process. So for example, we can determine the transition of the film growth mechanism in nanocrystalline diamond films. And also we can detect intra-film variations, as I've shown you on this last slide when we by purpose changed the plasma composition. And also we have a mean to extract the NNK from in situ reflectivity spectra in a batch process. And that's for my talk. Thank you for your attention, and I'm open to questions.
I remember this product has been announced in the ceremony of 20-year anniversary. 25 years last year. Yeah, I was online at that moment. So would that be able to get on market or something? Almost. Okay, looking for. Yeah, okay. So do we have any question to Dr.? Yes, please.
I'm just wondering on your measurement with the DLC films, you're probably restricted to a certain thickness, at least as long as you look for interference, because the coating itself is not transparent and you would need transparent films or a certain wavelength spectrum. So is there any upper limit or any boundary conditions you need to fulfill?
Well, we never hit that limit in this process, so we measured up to 1,000 nanometers, and this works. There are two limits, as you mentioned. There is this absorption limit. If there is the absorption, if all the light is absorbed within the thin film, then you don't have anything from the backside, and then the interference effect is gone. There is a second limitation that the frequency of those wiggles in the wavelength range is so fast or so dense that you would no longer resolve them with our spectrometer, and that would be another limit that you would hit, basically. But so far, we haven't seen any application where those two limits would have. Well, the second limit, we haven't seen any, never a process. And then the first limit, obviously, that depends on the film, on the refractive index properties, so the absorption, basically.
Following the questions, sorry to occupy your time. You know, I know you have a solution, but you know, DLC is considered as the dirty process in industry, and the chamber can be highly contaminated by those hydrocarbon absorption layer and blah blah blah. So how do you solve this problem? And so that would be the contamination to your collimator lens, and also another thing to consider is NCD, could be temperature. A bit of high temperature deposition, okay, and how your device can tolerate this high temperature environment.
So to the second one, this process was run at 450 degrees centigrade, I guess, and we had no problems, partly because the optics are outside of the vacuum chamber, so we don't see the full temperature of the process. And to your first question, oh, I'm going the wrong. Oh, I can do this. I mentioned it briefly. This device here was specifically done for a high deposition rate process, because normally we use those optics with a protection device, and we have those tubes where the light passes through. But the problem is that also the openings of those little tubes get coated by a high rate deposition process. And then you no longer, the intensity changes over the length of the process itself. So you get a sort of a wrong determination of the reflectivity. And this is why we developed this kind of device, where we actually measure the film gets deposited here on a transparent substrate. The optics is back here, and we measure from the backside through the substrate the film thickness. So the optics is actually protected by the witness glass itself. And so we cope with this problem in this way.
Okay, smart idea. And less than 50 seconds, do we have another question for our speaker? If not the case, thank you for Jan Peter. Thank you. And then our next talk will be given by Professor Qianren Tang, who will give us an alternative to high PIMs. As you see that there has been a trend moving the evaporation deposition towards sputter deposition for optical coating. and particular high PIMS process that seems like to be the next step for producing optical coatings. But Professor Chen Rentang in Department of Photonics, our university, he would like to propose the other methods that will plasma and the growth in separate zone. That's an alternative, and also show the variety of the coating in industry, and also the approach can be different through different ways. So let's give him a warm welcome.
Okay, thanks for Professor He's introduction. Sorry, maybe apology for my poor English and lack memory. So I stand here to make a note to remind me some content. Okay. Good afternoon, everyone. I'm Chen Tang from the Department of Photonics at Fongjia University. Today, I will be presenting our research on plasma-assisted reactive magnetron sputtering process for optical coatings. We hope could provide you valuable insights into preparation of high-quality optical thin films using assisted reactive high-pins process. I will first to introduce optical coatings thin film properties and deposition methods. Then I will discuss different process for reactive magnetron sputtering. Then I will give a summary. Okay. Excuse me. 画是不见了。没画是。哦，看到了。Okay. Optical coatings can be using ion-assisted electron beam evaporation method and magnetron sputtering or ion beam sputtering methods. These coatings have various applications, such as for optics displays or in the semiconductor industries, militaries, or commercial electronics and solar energy technologies. Specific applications include mid-infrared or far-infrared optics, head-up displays, or narrowband pulse filter used in technology such as Face ID or LiDAR for smartphone. Solar absorption coatings and anti-reflective coatings and low-E coatings for solar thermocorrect solar panels and glazing glass. Anti-reflective coatings can also be used to apply to metal for decoration or anti-counterfeiting purpose. In some scientific research, such as in advanced LIGO, low mechanical loss coating is important. Optical coatings are thin film deposited on a substrate, and they support multiple beam interference. They often have more than one layer and can be assembled using quarter wave and half wave layers. Interference filters calculus can be complicated and are typically done using computer programs. An example of optical coatings is anti-reflective coatings made of niobium oxide and silicon oxide films. The thickness and reflectance spectrum of each layer are shown in these two figures. However, if the thickness error of each layer is about 1%, the anti-reflective coatings spectrum of anti-reflective coatings may be not suitable for application. Therefore, the thickness error must be precisely controlled to below 1 nanometer or less. Optical films need to meet specific physical properties, including density, uniformity, low residual stress, low loss, and so on. A higher density gives a higher refractive index. Non-stoichiometric compounds and rough surface can cause thin film absorption, while an inhomogeneous film can lead to refractive index change with thickness, which complicates design multi-layer coatings that match the practical designs. To prevent film peeling or cracking, it's important to reduce residual stress and substrate deformation. In addition, optical film may need other properties like high hardness, high aberration resistance, high laser damage threshold, or specific crystal structure, and so on. Coatings are made by condensing vapor under vacuum using different processes such as thermal evaporation or sputtering. However, each process has its disadvantage. For instance, IAD process results in low film packet density and poor adhesion to the substrate. IBSD has lower deposition rate, low production yield, and high residual stress. Reactive electron sputtering is commonly used for optical coatings, but it also has drawback like slow deposition rate, particle contamination. Okay, these issues can be addressed with plasma-assisted reactive electron sputtering, which use different sputtering power supplies, such as DC, pulse DC, mid-frequency, or bipolar and high pins. The reactive high pins process has some issues, such as plasma instability, high arcing rate, and slow deposition rate of oxide or nitrides. These issues arise when a dielectric layer accumulates on the target surface, and high voltage lead to its breakdown. To solve these issues, three methods are proposed. Using a closed-loop PID control process for the hysteresis loop in the transition mode, and switching to a high-frequency mode by changing the sputtering power, or using a two-stage plasma-assisted reactive electron sputtering process. In this study, we used high pins to prepare thermochromic tungsten-doped vanadium oxide fins on a gray substrate at a low process temperature of around 300 degrees Celsius. Vanadium oxide is an excellent choice for thermochromic fins, but traditional methods require high substrate temperature of at least 400 degrees. High pins has used to help with crystallization due to its high kinetic energy and ion dissociation rate. The specific monoclinic crystal structure of vanadium oxide fins depends on the oxygen flow rate during sputtering, as shown in this figure, indicating the optical emission spectrum of vanadium plasma. We used the step-by-step hysteresis test of vanadium ion emission line at 310 nanometer with varying oxygen flow rate in precise PID algorithm for control. The figure shows the hysteresis curve for the vanadium ion emission line with set point for 75%, 70%, and 60%. The Ziegler-Nichols method was used to calculate PID parameters, and the evaluation is demonstrated in these figures. The process error was found to be less than approximately 1% of the target value during 45-minute process. We observed the that adding tungsten doping reduces the critical temperature and the change in transmittance from 65 degrees to 35 degrees Celsius, and from 43% decrease to 39% respectively. We also fabricate a thermochromic device, which is shown in these figures. The change in transmittance can be affected by the ambient temperature and by heating the aluminum zinc oxide film with an applied voltage. In our previous research, we were able to make silicon oxide nitride gradient index Luger filter using a reactive pulse DC magnetron sputtering with PID closed loop sputtering voltage control. We found that the measured transmittance curve matched well with the theoretical design. We also used the PEM with closed PID control in reactive high-pins process to make optical multilayer coatings. During the process for aluminum oxide nitride fins, we measure the intensity of the aluminum emission line as we increase the upstream flow rate from 0 to 1.6 SCCM. We calculate the PID parameters for upstream flow rate ranging from 0.8 to 1.2 SCCM, which are displayed in this figure. The filter has 301 layers with physical thickness of 3.2 micrometer. It means the sinusoidal wave distribution for 3.2 micrometer. The first and the last 59 layers are a partition layer. The refractive index of the remaining layers are distributed in 18 cycle quasi-sine form. The refractive index of each layer will control using PID plasma emission monitoring as shown in the figures. However, the last two figures show the more arcing occurrence. The Luger filter's central wavelength and the bandwidth were close to the theoretical design. And the PID closed loop PEM system can be used to control the process. However, the arcing and the melting macroparticle ejection occurred, resulting in poor transmittance spectrum performance and light scattering from the defect surface. Therefore, the refractive index, reactive high pins process for aluminum oxide nitride fins was not suitable for optical coatings. The metamorph sputtering technology was proposed by Oakley in 1989 for advanced optical coatings in mass production. Since then, several companies and research institutes such as Synchron, Alvec, Opron in Japan, Dayong in Taiwan, Fraunhofer IST and Buller Libel Optics in Germany, Evatec in Switzerland have developed this technology further. In our lab, we have built a plasma-assisted reactive magnetron sputtering system that can vary the sputtering power using different modes, including DC pulse DC high pins, combined high pins with mid frequency, including deep oscillation magnetron sputtering, plasma-assisted reactive pulse DC magnetron sputtering, and plasma-assisted reactive high pins. We have also developed our own ICP system for compound reaction. To precisely control the optical layer thickness, we have developed a hybrid optical monitor system that covers both broadband and single wavelength monitoring techniques. Additionally, we have developed a thin thickness distribution simulation program using Level software, and some parameters are simulated using the commercial software console multiphase. The table lists the parameters for different modes of sputtering, such as high pins MF with MF, DOMS, and PDMS. The table also lists include the on-off time and the power of pulse superimpulse in high pins. Three figures shows the discharge voltage and the current waveform for different preparation process for aluminum oxide. The table lists the parameters used for deposition aluminum nitride and aluminum oxide film by plasma-assisted reactive high pins and plasma-reactive PDMS process. A separate ICP region was utilized to deposit the dielectric film reactively and avoid target poisoning during the metallic film deposition from the aluminum sputtering target. Arcing count increased with deposition time for aluminum oxide deposited by high pins and superimpulse, while no arcing counts were observed in other processes. Most of the aluminum oxide films prepared by various deposition methods were almost homogeneous and amorphous. However, the film prepared using high pins process exhibited more arcing, resulting in light scattering from a rough surface. The inhomogeneous aluminum nitride films prepared by high pins were due to random imprint orientation of crystal structure crystal growth, while aluminum nitride film prepared by plasma-assisted reactive high pins and plasma-assisted reactive PDMS showed homogeneity due to the crystal structure exhibited strong 002 diffraction peak. The aluminum nitride film produced with superimpulse high pins with MF, DOMS, and PDMS may have a slightly inhomogeneous structure due to low kinetic deposition during deposition. The figure shows the optical constant and the physical properties of aluminum nitride and the aluminum oxide films. The aluminum nitride and the aluminum oxide films deposited by PDMS and has the lowest residual extinction coefficient and residual stress. The plasma-assisted reactive high pins process was chosen for stable process, homogeneity, okay, and maybe have a good property for the process and extinction coefficient around 10 to -4. The notch filter of aluminum nitride and the aluminum oxide film by this process and the physical signal is shown in these figures. The high pins notch filter has lower transmittance and large particle on the surface. The plasma-assisted reactive high pins and the DOMS has the more good performance for transmittance performance, for good transference for performance. The plasma-assisted reactive high pins has the clearest surface compared to the DOMS filter. Okay, in conclusion, different processes can modify film properties for various optical coatings application. DOMS and the plasma-assisted reactive high pins process prevent arcing during aluminum oxide film deposition. Plasma-assisted reactive high pins is suitable for high-quality aluminum nitride and aluminum oxide films for optical coatings. Finally, we want to thank Dayong Company for their financial support and commitment to scientific research. And thank you for your attention.
Thank you, Professor Tang. Do we have any questions to him? I think you need to have a lot of optical professional knowledge to ask questions, including me. Loop gate filter and the notch filter or whatever, that's really difficult for us. Perhaps, oh yes, Ralph, please.
So you mentioned on the different ways, and you already showed that the plasma-assisted reactive high PIMS gives the best results. So the way what you described, either using the DOMs results in good quality. What is your way or your recommendation for optical systems with high PIMS? Because you mentioned already that the K values are quite high. You get some defects or some problems with the film quality. How to avoid this quality issues in high PIMS?
I think first the DOMS, DOMS and those process have lower arcing or no arcing can be observed. So I think we can avoiding arcing occurrence, and we want the higher kinetic energy to form the homogeneity fins and the low absorption. So we wanted the structure more. We know aluminum nitride easy to grow some kind of a crystal structure. So if you use high pins, maybe have high kinetic energy, so can form many different orientation in the fins. So in random in plane orientation may be due to the more inhomogeneity. So, but we use the plasma-assisted reactive process. We can see the only 002 crystal structure, the diffraction peak. So maybe the thing more homogeneity than other process. So we can use those processes to have high homogeneity and high refractive index and low absorption. But for DOMS, this process maybe no arcing and but we maybe lose some kinetic energy. It's lower than plasma-assisted reactive high pins or lower than high pins. So maybe the fin property more close to the pulse DC magnetron sputtering, so have a slightly inhomogeneity. Okay, so we chosen the plasma-assisted reactive high pins because it has a higher refractive index for aluminum nitride. The blue color is the aluminum nitride. Purple color is for aluminum oxide, and maybe has little higher than other PDMS processes. The extinction coefficient little higher, but it maybe close to 5, 10 to -4. So we can accept as extinction coefficient value, and but it has the lowest surface roughness, and maybe higher, the residual stress higher than PDMs, but maybe it also quite small than others. So, and have higher deposition rate. Okay, so I think this is a better process than DOMS, and maybe some particle issue for high pins is very serious, but for DOMS have a little particle can be measured on the surface. But for plasma-assisted reactive high pins, I think this is a clearest surface. Okay, so I think the plasma-assisted reactive high pins is a good choice for optical coatings. Okay.
per second. So this will help to reduce the arcing damage. The others is the current. For example, Trump Hoodinger power supply is a current regulation. So when we power on the current, the current will go up very quickly and sit at the setting value. So like a rectangular pulse of the current. So this kind of current stable at a setting value will prevent arc happen during the process. So this that contribution from power supply.
But power supply, to modify or to improve the power supply always help. But for reactive magnetron sputtering, the target surface oxidation is very serious, even for other process. But for aluminum target or silicon target, the reactive or poison is needed to consideration. I think just change power maybe not useful. So we use the plasma source to reactive the fin and keep the target and all sputtering region clean. So no arcing will occur, no oxidation will form on the target. So I think it's a better process for direct reactive magnetron sputtering process. Okay. Yeah, maybe. But I think the power supply always can provide more high energy or other benefit for process. So I think to develop a new power supply is very important. Okay.
Thank you. Yeah, ladies and gentlemen, very thank you for this time. And if I were not wrong, I think it should be the closing ceremony right now. Yes. So I should shorten my presentation. Yes, there's some limitation from General Manager Yang. He just told me that don't say too much about the product of ABEC. And I should not say, should say something very short. And the last one, I should have some introduction for him. So that's why he just asked me to say the trend for everything. So yes, I was born in, I was born in 1971, and it just is that's the same year when I think there's another speaker, Professor Kawai. He received his doctorate at this year, and I graduated from Tsinghua University, major for the material science. And yes, I do the military service, but it's not because of that, so I lose my teeth. And then, yes, I graduated from the Tokyo Industry Technology. But yes, just like Jiao Da, it combined with a medical university, so it changed the man. And yes, ABEC is my first work until now. So I work for ABEC for more than 22 years. And my hobby is reading classic music. And yes, I go to Taichung. It's my favorite city in the world because I'm the fan for the best baseball team brothers. So I was go here and yes, go to see the baseball with my family. Yeah, not she. This is my family. Yeah. To prevent any misunderstanding. Yes, just the study. So why I'm stand here and introduce for that because yes, Yang hold me to say that why ABEC actually it is a giant for the electronic deposition system. So I will have a very little introduction. Yes, there's no product here. So yes, we have 241 billion Japanese yen, and yes, the exchange rate shift a lot, but it's around something like 2 billion or something for the United States dollar, and 80% belong to the equipment. And next stop. Actually, equipment vendor grows as the society change. So I will not talking about our product, but I will talking about what our equipment do for the product. So you can see that in the 1990s, there's a lot of semiconductor that is very old-fashioned. You can see that 1 mega of the DRAM that's produced by Toshiba or something like that time. And then we have a very old-fashioned LCD. At that time, everybody just said just 2 color, black. You should say like green or dark. Yes, then shift to nowadays LCD, and we put it into the flat panel display as our TV. Then we can see the new era for the semiconductor. So we can see that recently we're talking about the EUV, we're talking about FinFET, a lot of things, and our business grows as a society change. So from the next page, I will say that ABEC is really a strange company because, you know, this six gentleman is our founder, and this one actually he's very famous. He's just doing the Asahi beer, you know, the Asahi beer. The president of Asahi beer also invests in our company. So, yeah, a little bit weird, but from our product, you can see that. Yeah. You know, when you're talking about innovation, you should be crazy. And a legally way to drive you crazy to drink beer or alcohol. Yes. Yes. Yeah, but not tonight. But not tonight. Yep. So in 1952, yes, we have very old-fashioned for light coating for a reflection of the light. And today we also talking a lot of the light, but yes, it's the same the light, but we're talking in different scale. If we're talking in different scale, then things change a lot. So I will point about that around 1970s, not because I was born in 1971, but you can see that at that time our product is just the same for the coating that we talk today at this time. But after the 70s, we just go to another direction that we just first focus on the electronics. So we have, yes, it's very old-fashioned LCD, and yes, this kind of the. I think the student in the side don't know what is floppy. Yes, that's very old, but we just use a floppy. And you know, when we say a floppy is too old, then there's a CD-ROM, but it's all gone. So we do the electronics, we face a lot of the risk, but it changes a lot. If you catch the trend, then you can earn a lot. So before I go to the stage, I just heard that you have your product and go into the industry for maybe more than 25 years or something. But the most successful product for ABEC is for the flat panel display. We have the first patent in 1982. I mean, when you got a patent in 1982, you should have some research in 1970 or something. But when we sell a lot and make it into our most important product, it's around 2000. So the same as you. Our product from research to the main product, we also go for more than 20 years. Yeah, so that's why I would say that the trend for consider our business is very important. So I would like to say why we're just doing something good and everybody say that semiconductor is very important for Taiwan, blah, blah, blah. And why I'm here and want to have some cooperation to finding some new coating area. So first one, I was talking about something that happened in the semiconductor equipment market. And the second one, I would say that we just remember the word keyword SAVE, S-A-V-E. And it's talking about sustainability and talking about automation, talking about variety, and also something about the energy. So from this kind of background, we can understand why there is a change for such kind of the researcher and the company get involved into this field. That's nature, not what you want to do, but it's nature. The trend will go into this way. Okay, so yes, this presentation from Applied Material. The same thing, you just said that, oh yes, we just going grow and in a sharper way from the PC and to the mobile, then to the AI. But the real thing is that for selling the equipment, the product itself is growth, but equipment, it is not. So you can see that, yes, we have a very good bad downturn in 2019 for -7%. And yes, in the beginning of 2022, everybody just said this will be the best year forever. It is in February or something. But in June, they just say, oh no, it will be the worst of the year in the history. Yeah, just, you know, at that time when we have equipment receive the PO, and then the lead time will be more than 1 year. So, but the economic situation changes within 4 months or 6 months. And as there is an electron market, late 70s of the downturn. So yes, we just see that. In last year, everybody just said that we need some talent, and there's no talent in Taiwan and something. And this year, they just say, oh, we will let off some talent. Yeah, so that's why we see in the electronic market. So it's, yes, you can gain a lot, but you may also lose a lot. That's the characteristic of this kind of the market. But so for the semiconductor, actually, there's 4 things to drive it, keep on growth. Everybody knows that, especially for Taiwan, that is for the performance and also the cost. So we also say the CP value. Yes, and in talking about semiconductor, because we should put every transistor into very small areas, so we will change it into the area cost. But for the AI, we should pay attention to another keyword, power. I know that the German for this winter is very disaster because your electric fee will increase by 5 times or 6 times. Yes, very terrible. You know, in Taiwan, the weather is hot, but no one will die. But in winter, yeah, it's serious. When it's under the 30th degree for more than -5 or 10, it's something related to your life. But still, it may increase them 5 or 10 times. So Yes, actually, right now we add another benchmark. We say that power, and another way is why Japanese lose their market is because that the speed for Japan is very slow. So time to market. Actually, it's from a premature two, and they just say that PPA ACT, the performance, power, area cost, and time to market. And I will to address this power because it will happen in my presentation later on, and repeat it again and again. So, yes. So we talking about the background for the semiconductor. Yeah, it's hugely change. And another one is that if you get all the things, you can win a lot for EUV, for SML. But if you lose, you are nothing. So, but coating is not like that. Why? Because I will explain something that why we need coating. As we study from the material, actually we just hope that the world will not be perfect. If the world is perfect, then the water will not freeze in the 0 degree, but maybe under 8, 15 or something from my textbook. Yeah, so yes, the world is not perfect, but if you want it to approach perfect, how do you do? You can do in the coating to make it approaching the perfect. So yeah, that's actually we do. No perfect material, so we do in the coating. So this fourth thing is, I think that will very important and influence the coating world in the future. The first one is sustainability, but I will talking it as the COO. And another one is automation. That's what we just see today. Yes, and I just see in the presentation in this morning at the beginning that say that our automation just from to move the robot arm. And right now, not only the robot arm, we just begin to judge. When will we begin the deposition? When should we increase the gas? When will we change the pressure and something? But it all depends on we got the eyes. That's what the excellent company just do a lot of things to monitor the plasma and something to have the eye, and we can do another automation just from the movement and to judgment. Then another way is also what we learn from the material science. We call it the entropy. Everything it will go into chaos. So at that time, we need more and more element and combination. So we see that there's a high entropy alloy there. Yes. So I would say this is nature. And another one is that why there's electronic film and also the hard coating film, because the energy for the plasma is totally different. So I would say this fourth thing is what I want to say today. And actually it's the conclusion, but I will show some photo because I think there's no time there for me. So let's say the PPAC, but with the AI, we can do a lot of things, not just only that I can do a process well, but we can shorten the time, we can shorten the time for the installation, and we can increase the yield. As not, we just have a one-shot good, but we can keep it very stable with the totally automation control. But as I have mentioned that, energy talking about, so it's the key trend for the data generation. And you can see that actually it's increased from the 1952 to 22. It's just 70 years, and increase for, yes, the digital will be more than 20 or something. And for the variety, we also have a different generation in different ways. So there's no way for human to deal with such kind of the different data. So that's why we need a lot of the AI. Yep. And yes, so I still say that power is very important. Yes, we deal a lot of AI means that we should consume a lot of the energy. So that's where the memory that we should consume. And yes, the chat GTP is very famous recently. And you can see that just within several years, we from GPT-3 to the most new one, GLAM, it will increase by 1 digital. Yeah, it don't mean that we need a lot of energy. So still, if we want to do a good equipment, we should understand how to reduce the yield. Because if we reduce, just have said that there's a 7 waste. Eliminate the waste, then we can have a high efficiency for this. And the entropy will come easy. Just means that the other thing is, so don't clean your house. It's in vain. Yeah. So, but it's really happened in the semiconductor industry. So you can say that from 1980s, we just use a real semiconductor. I mean, the race for the 4 and the 5 and some of the 3. So it's just here and some outside fluoride in 80s. But to the 90s and 2000, we use almost all the element in the periodic table. That's why I think high entropy alloy is a way that will not change because it's nature. So still another way is that we will change the form. So we can see that we have the optical monitor and not in the flat surface, but also in the curved surface. And that's what we see for the real product. And yes, first time I just think that this is just a drawing, but actually it's true. So I think it will be very near years we can see this kind of new product in the future. And that's an example in ARBEC. Actually, we have some equipment that just have loading the substrate for more than 3 meters, just like this. And our OLED equipment will get it and more than 50 meters. So yes, you see that, you will say, wow, this is a great company. But if you cannot sell, sometime when the market is saturation, then this will be a disaster. So that's why I just want to learn from GM Young. Maybe we can cooperation and find some stable business. Yep. So the last one thing is that when we go into the electro device, we just want to reduce our energy. So from the spotter, then we go to the CVD. Then, talking about CVD, we need a surface energy. Then we need the ALD. It not only the surface energy, but also some ionic energy there. So yes, that's what we do in this area for UVAC, for the last one. But for the hot coating, we just go in other way. So today we just see that we need a lot of the high voltage and something like that. So we will meet the nature for the arcing. So how to reduce the arcing and then keep on the production. It's also the first topic that we talk about, the sustainability, the COO. Then we will train too. So that's what we do. So we need small energy. But you know, the Garmin watch, you can scratch on the stone and something, and very strong connection between the film and the substrate itself. That's also another top technology. Everybody just think that this is very tiny and very advanced technology. But in the other way, this is true. So gentlemen, you are also doing a very great work right now. Yeah, so this is ARBEC, which is doing the vacuum, and I would like to appreciate for the Professor He and the GM Young. Actually, when I see that with this kind of topic, actually we're just talking about a great company that know their trend and holding this kind of conference for everybody to get together. Thank you. This is my presentation.
I find an excuse to convince my wife not to clean the house. and also, I try every day to clean up my desk as much as I can. But apparently there's no longer to do that.
Just pay attention. There's some student there.
Oops. Okay. Yeah. Okay.
Yep.
Apparently, we already see this talk with prophecy inside, and I think we learned a lot from this talk, as well as all our speakers today. So, do we have any questions from our audience? Sorry. Okay.
Yeah, maybe just a comment, not a question. Now you are Ulvak, like a
Yes,
giant,
right.
you know. We are the dwarfs, the twins, small ones, you know. But it was very good. No, but what I wanted to say is it was very good actually, and it brings also as a small company as forward. If you say even Ulvak is sometimes in their business going up and downs, and you have to overcome these problems. You have to stay with this. I think the same with Dayong, and that is very important.
Yes,
and
right.
I'm also thinking that Ulvak, even if it's a big company, they need some, not really support, but they need more companies to bring new innovations and so on.
That's right.
So that's was very nice in your talk. You know,
Yeah,
so
thank
thank
you.
you for that. You know, and this brings also my small companies give us how do you say this in English? It gives us a motivation to move
Yes, right.
forward, and even in hard times, just go on, because all what you said, I think, will more or less come true and come to a good end.
Yeah, yeah, that is like true. So that's why I'm here. And actually, you can understand that when we begin this kind of when we begin the FPD business at that time, around the 1980, the main product will be the CD-ROM or something. So at that time, we should try to find a small seeds and working together. Yeah, in the past way, Japan is just saying that they can do everything. But right now, they just think that we should cooperate to make everything. So it's very great to see you today in Taiwan. Yeah.
Thank you.
Thank you.
I want to comment to you. How do you explain your wife? You do not have to clean your house. Good job.
You're only half correct. But, I mean, you only half correct because I always have to clean the chamber. Okay. We are expecting the everlasting talk from today, but the time. But anyway, we will try our best to go to next forum as quick as possible, because our friends has already asking when will be the next. Yeah, and of course your great contribution from our speaker, from our organizer, sponsors, and therefore there's a little bit ceremony for saying thanks to them. And you, as you have seen that our organizer, our co-organizer, and also our sponsors. Thank you for your generosity and your contribution. Perhaps we have some formal thanks from our, please.
请各位跟我一起感谢今天论坛所有的演讲者以及这次论坛的工作人员。由于他们的辛苦，才能让论坛顺利的完成。他们都在后面向大家挥手，我们掌声谢谢他们。此外，我们也感谢本次的论坛赞助厂商 Plasus GmbH、优贝克科技股份有限公司、量子讯息有限公司、利宝来科技股份有限公司、爱德华先进科技股份有限公司、台湾来宝股份有限公司、兆军光学股份有限公司、玉兴机械企业社、硕印企业股份有限公司、应用奈米科技科技股份有限公司、松汉股份有限公司、合作金库商业银行中权分行。最后，再次感谢您的出席，使本次的论坛蓬荜生辉。希望很快与您再见面。感谢各位，谢谢。
English. I will repeat our sponsor again in English. Plaza's company, UVAC Taiwan, And the quantum information, liberal technology, Edwards technology, Libo Taiwan, Terra Optics, Yushin Machinery Factory, Shuoyan Company, Applied Nanotechnology Science, and Songhan Company, Taiwan Cooperative Bank, Jianghua Branch. Thank you very much. And let's give yourself a thank for your attending a company with us all today. Thank you very much. Thank you. And goodbye.
Please remember to take your personal belongings with you.